Kellogg's, Cheerios, and Frosted Flakes are breakfast icons found in millions of kitchens around the world. But behind every crunchy bite is a massive factory operation that turns grains into perfectly toasted and flavorful cereal. Today we're going inside the production lines to reveal exactly how these classic cereals are made from start to finish. It all begins with the raw materials. For Kellogg's cornflakes, the primary ingredient is whole grain yellow corn, chosen for its high starch content, consistent kernel size, and clean flavor profile. The corn is sourced from farms that meet strict quality standards, often grown in regions where soil conditions, temperature, and moisture levels yield the optimal crop. The grain suppliers must pass multiple certification checks to ensure there are no contaminants, pesticides above allowed thresholds, or off-spec kernels. Alongside the corn, other ingredients such as sugar, malt flavoring, and a precise blend of vitamins and minerals are procured from certified ingredient suppliers. Even minor ingredients undergo laboratory testing for purity and safety before they are ever allowed into the production flow. When the corn arrives at the Kellogg's plant, it is unloaded from bulk transport trucks or rail cars into massive silos. These silos are fitted with aeration systems to keep the grain dry and prevent mold growth. Before storage, the corn passes through a preliminary cleaning system. This includes vibrating screens to remove large debris, aspirators that blow away dust and light particles, and magnetic separators to capture any stray metallic fragments. The cleaned corn is then weighed using automated bulk scales, ensuring precise tracking of raw material usage for both production planning and regulatory compliance. From storage, the corn moves toward the first processing step, cooking. But before cooking, the kernels need conditioning. This involves sending them through a pre-wet process in which they are steamed lightly or soaked in warm water to raise their internal moisture content to the right level for even cooking. Moisture meters along the line continuously monitor this process. Once conditioned, the kernels are conveyed to large pressure cookers, sometimes referred to as steam cookers or rotary pressure vessels. These massive stainless steel cylinders rotate slowly while injecting steam and adding a carefully measured solution of sugar, malt flavor, and salt. The steam not only cooks the kernels, but also helps the added flavors penetrate evenly into each piece of corn. The cooking process gelatinizes the starch inside the kernels, making them ready for the next transformation. After cooking, the hot, softened kernels need to be cooled and partially dried. They exit the cooker onto a series of vibrating cooling conveyors where ambient or slightly chilled air is blown across them. This stops the cooking process, stabilizes the texture, and prepares them for the critical flaking stage. However, the corn is still too moist to be flaked properly. It first enters large industrial dryers, often drum style or fluidized bed dryers, which reduce the moisture content to an exact level that will allow the flakes to shatter cleanly, rather than smear or tear during rolling. The drying process is closely monitored by moisture probes and computer-controlled exhaust systems to maintain uniformity. The next stop is tempering. Tempering involves holding the cooked, dried kernels in large bins for several hours so the remaining moisture distributes evenly throughout each kernel. This equalization is key to creating flakes that cook evenly in the final toasting step. The bins are equipped with gentle agitators or slow conveyors to prevent clumping and to keep airflow steady. Once tempered, the kernels are ready for the flaking process. Here, they pass through massive flaking mills. Each mill consists of two large, precision-ground steel rollers, often cooled internally to prevent heat buildup. These rollers press each kernel flat in a single pass, creating the familiar, thin, oval shape. The gap between rollers is set to a fraction of a millimeter and is adjusted automatically to ensure all flakes have the same thickness. The flaking mill is one of the most critical pieces of equipment, because the thickness of the flake determines not only the texture, but also the way it will toast and absorb milk later on. Freshly flaked corn is still pale and slightly soft, so it moves immediately into the toasting ovens. These ovens are long, multi-zone conveyors where hot air, often at temperatures over 300 degrees Fahrenheit, flows over and through the flakes. The first zones drive off remaining moisture, while the later zones caramelize the sugars and develop the golden brown color. The toasting stage is where the signature crunch develops as the starch matrix hardens. The aroma at this point is unmistakable. Warm, slightly sweet, and distinctly cereal-like. Automated sensors monitor the color and moisture level, and adjustments to air temperature or conveyor speed can be made in real time to maintain consistency. Once toasted, the flakes are cooled on open conveyor belts with filtered ambient air. Rapid cooling helps lock in crispness and prevents condensation inside the packaging later. At this stage, the cereal may pass under a vitamin and mineral application system. In some Kellogg cereals, a fine mist or powder of fortified nutrients is sprayed or dusted onto the flakes, then gently tumbled to ensure uniform coating. The application rate is measured to fractions of a gram to comply with nutritional labeling requirements. From here, the flakes head toward the packaging. Before they can be boxed, the cereal is screened to remove overly small particles or broken flakes. These screenings may be collected for use in other products or as livestock feed. The main product stream passes through a final quality check, which can include metal detectors, optical sorters, and even X-ray scanners to detect any foreign matter. Samples are pulled at regular intervals and sent to an on-site lab, where technicians test for moisture content, color, flavor, and texture to ensure the batch meets Kellogg specifications. The packaging line is a marvel of precision. The cooled cereal is metered into form-fill seal machines or pre-made bag fillers. In the classic box format, an inner bag made of food-grade plastic film is formed from a continuous roll filled with an exact weight of cereal using high-speed scales, then heat-sealed. The filled bag is automatically inserted into a printed cardboard carton, which is glued shut and stamped with a production code for traceability. Packaging machines operate in perfect synchronization with the upstream production flow to prevent overfill, underfill, or product jams. Sealed boxes travel down conveyors to be bundled into shipping cases. Robotic case packers arrange multiple boxes into corrugated cardboard cases, which are sealed and labeled with both barcodes and batch codes. These cases are stacked by robotic palletizers into tall, stable loads, often wrapped with stretch film to secure them for transport. From the moment the corn arrived at the plant, the environment has been strictly controlled for food safety. Air is filtered, surfaces are sanitized regularly, and all equipment is cleaned in place using automated cleaning systems that circulate hot water and food-safe detergents through the machinery. Employees follow stringent hygiene protocols, including wearing protective clothing, hairnets, and gloves. Every step in the process is documented for traceability, so that in the rare event of an issue, the source can be identified and contained quickly. Once the pallets of finished cereal leave the plant, they are loaded into clean, dry trucks or shipping containers. Distribution centers receive the pallets, store them under controlled conditions to prevent moisture pickup or crushing, and coordinate shipments to retailers. Retail stock rotation ensures that consumers always get cereal at peak freshness. The shelf life of cornflakes is typically several months when stored in a cool, dry place, thanks to the low moisture content and protective packaging. Beyond the basic process, Kellogg's has invested in continuous improvement and technological innovation in its plants. Automation now allows for real-time monitoring of every parameter, from the temperature inside the toasting oven to the precise thickness of flakes coming off the mill. Data analytics can flag trends before they become defects, enabling preventive adjustments. Energy efficiency measures such as heat recovery from ovens and optimized air handling systems have been integrated into many plants to reduce environmental impact. Cheerios production begins long before the famous little toasted oat rings take shape on the factory line. It starts with selecting the right oats because in a product like Cheerios, where oats are the star ingredient, the raw material defines the flavor, texture, and nutritional profile. The oats are sourced from farms that grow specific varieties of whole grain oats prized for their uniform kernel size, high beta-glucan content, and consistent milling performance. These farms are often located in cooler climates where oats thrive, and the crops are harvested, cleaned, and transported in bulk to the manufacturing plant under strict quality control conditions. When oats arrive at the facility, they are unloaded into massive storage silos equipped with aeration systems to maintain dryness and prevent spoilage. Before being accepted into the main storage bins, the oats pass through mechanical cleaning systems. These systems remove dust, small stones, and plant debris using vibrating screens, air aspiration units, and magnetic separators that capture any trace of metal contamination. Every incoming lot of oats is also tested in the plant's quality control lab for moisture content, protein level, microbial safety, and the absence of unwanted residues. The next step is oat milling. In the Cheerios process, oats must be transformed from raw groats into a workable form for extrusion. This begins with dehulling, which removes the outer husk from each oat kernel. The cleaned oats are fed into impactor hullers, where centrifugal force cracks the hulls without damaging the inner groats. The hulls are separated from the groats using aspiration and gravity tables, and the groats proceed to a kiln for heat stabilization. Heat stabilization is a controlled toasting step in which the groats are gently heated to deactivate enzymes that can cause rancidity. This step also enhances the nutty flavor of the oats. From there, the groats are rolled or ground into oat flour. For Cheerios, a blend of whole oat flour and sometimes additional grain flours like cornstarch or wheat starch is used to create the right dough properties for extrusion. The oat flour is measured precisely, and minor ingredients such as sugar, salt, and a vitamin mineral premix are prepared in separate dosing hoppers. All these dry ingredients are fed into a pre-mixing system, where they are blended into a uniform mix before moving to the wet mixing stage. Wet mixing takes place in an industrial preconditioner or mixer, where water and sometimes steam are added to the dry mix. This creates a damp, pliable dough. The ratio of water to dry mix is carefully controlled because it determines how the dough will behave in the extruder. Sensors inside the mixer continuously measure dough temperature, moisture, and homogeneity. This hydrated dough is conveyed immediately into the heart of the Cheerios process, the extrusion system. Cheerios are made using a rotary die extruder. The dough is fed into the extruder barrel, where rotating screws knead and compress it under controlled heat and pressure. The barrel is divided into zones, each with a specific temperature and mechanical shear setting. As the dough moves forward, the heat and pressure partially cook the starches and gelatinize them, creating a texture that will puff slightly when released from the die. At the end of the barrel, the dough is forced through a die plate that has hundreds of tiny, ring-shaped openings. Each opening has a small pin in the center, creating the hole of the Cheerio as the dough extrudes around it. As the dough emerges from the die, it is cut to size by high-speed rotating knives mounted just outside the plate. The freshly cut rings are soft, warm, and slightly expanded. These rings now enter the drying and toasting stages. First comes the primary drying conveyor, where warm air is blown over the pieces to reduce moisture and prevent sticking. After this initial drying, the Cheerios are transferred to large, continuous toasting ovens. These ovens operate with multiple temperature zones. In the early zones, moisture is driven off steadily, and in the later zones, higher heat creates the light brown toasted color and enhances the flavor through Maillard reactions. The toasting step is critical for the signature crunch of Cheerios. Moisture sensors and color cameras monitor the product as it travels through the oven, and computer-controlled adjustments are made on the fly to keep the output consistent. After toasting, the Cheerios must be cooled before packaging. They move along cooling conveyors where filtered ambient air is circulated. The goal is to bring the product to a stable temperature, so condensation will not form inside the packaging. This also allows the texture to set fully. In some varieties, a light coating of sugar syrup or flavoring may be applied at this stage using a rotating drum or tumbler. But for classic plain Cheerios, no additional coating is added after toasting. Next, the cooled cereal is sifted to remove small fragments or broken rings, which are collected for use in other applications or for animal feed. The main product stream passes through a final quality control system that includes metal detection, weight checks, and sometimes optical sorting to ensure that every piece is intact and meets size specifications. Samples are pulled for sensory evaluation, which includes tasting for flavor, checking crunch, and verifying that the shape and color meet the brand standard. Packaging begins with precise weighing. Multi-head weighers dispense exact amounts of cereal into form-fill-seal bagging machines. In the classic box format, an inner bag is formed from a roll of plastic film, sealed at one end, filled with cereal, and then heat-sealed at the top. Automated arms place the sealed bags into pre-printed cardboard cartons. Each carton is glued shut and stamped with a lot code that contains information about the date, time, and line of production for traceability. These cartons travel along conveyors to case packers, where machines arrange them into corrugated shipping cases. The cases are sealed, labeled, and then stacked onto pallets by robotic palletizers. The pallets are wrapped in stretch film for stability during shipping. Finished pallets are stored temporarily in a distribution warehouse with temperature and humidity controls to preserve product freshness. From the distribution center, the pallets are loaded into clean, dry transport trucks and shipped to retailers nationwide. Retail stock rotation ensures that older product is sold first, keeping Cheerios at their optimal freshness for consumers. The shelf life of Cheerios is generally several months due to their low moisture content and protective packaging, but quality is highest in the weeks immediately after production. Throughout the entire process, food safety and quality assurance are paramount. The factory environment is designed for easy cleaning and sanitization with enclosed systems that protect the product from airborne contamination. Employees follow strict hygiene protocols, including wearing hairnets, gloves, and uniforms, and undergoing regular training in food safety practices. Many parts of the plant operate under hazard analysis and critical control points plans, ensuring that every stage, from raw grain to finished package, is monitored for safety risks. Cheerios production is also heavily automated, with control systems tracking hundreds of variables in real time. Data on dough moisture, extrusion pressure, oven temperatures, and packaging line speeds is logged continuously. This allows operators to detect subtle deviations and correct them before they impact the final product. Over the years, the efficiency and precision of Cheerios manufacturing have improved dramatically through advances in automation, ingredient handling systems, and real-time quality monitoring. The making of Frosted Flakes begins with one key ingredient: corn, but not just any corn will do. The factories that produce Frosted Flakes work with carefully selected varieties of yellow dent corn that have the right starch composition, kernel size, and moisture profile to create large, uniform flakes with a crisp bite. These corn varieties are grown in regions where climate and soil conditions produce consistent, high-quality harvests. Before a single load of corn is accepted, it must pass rigorous inspections for moisture content, kernel integrity, absence of mold or mycotoxins, and overall cleanliness. This ensures that, from the very start, the product's signature taste and texture are protected. The corn arrives at the plant in bulk trucks or rail cars and is unloaded into massive storage silos. These silos are fitted with aeration systems that keep the grain cool and dry to prevent spoilage. Before the corn can be stored, it is cleaned using a series of mechanical processes. Vibrating screens remove large debris, aspirators blow away dust and lightweight particles, and magnets capture any stray bits of metal that may have entered during harvesting or transport. After cleaning, the corn is weighed using bulk scales, allowing the plant to track exactly how much raw material will be processed into frosted flakes. Once the corn is ready for production, it is first conditioned. Conditioning involves soaking or steaming the kernels to bring their internal moisture to an optimal level for cooking. This step softens the kernels and helps them absorb flavors more evenly later in the process. The conditioned corn is then fed into massive rotary pressure cookers. In these cookers, the kernels are tumbled slowly while being injected with live steam under pressure. A syrup blend of sugar, malt flavor, and a pinch of salt is added, infusing the corn with a sweet, malty taste that will deepen during toasting. This cooking stage gelatinizes the starch inside the kernels, transforming them from hard grain into a tender, flavor-packed base. When the cooking cycle is complete, the hot softened corn is discharged onto cooling conveyors where fans blow ambient or slightly cooled air over the kernels. This halts the cooking process and stabilizes their texture. At this point, the kernels still contain too much moisture to be flaked properly. They move into large industrial dryers, either drum style or fluidized bed designs, that gradually remove water until the kernels reach the precise moisture level needed for flaking. The drying process is tightly controlled because too much drying will cause the flakes to crumble, while too little will cause them to smear or tear during rolling. After drying, the corn undergoes tempering. This step involves holding the kernels in large bins for several hours to allow the remaining moisture to distribute evenly throughout each kernel. Tempering ensures uniform flaking and helps prevent uneven toasting later. Gentle agitators or slow-moving conveyors in the bins keep the kernels from clumping together while promoting even airflow. Now comes one of the most important steps in the frosted flakes process: flaking. The tempered kernels are fed into massive flaking mills where pairs of enormous, precision-ground steel rollers press each kernel flat in a single pass. The rollers are often water-cooled internally to prevent heat buildup, which could cause sticking or premature cooking. The gap between rollers is adjusted with extreme precision to produce flakes of consistent thickness. This thickness is critical. It determines how the flakes will toast, how they will break in the mouth, and how long they will stay crisp in milk. Freshly flaked corn is pale, soft, and flexible, so it immediately enters long toasting ovens. These are continuous conveyor ovens with multiple heating zones. In the early zones, hot air drives off remaining moisture, locking in the flake's shape. In the later zones, higher heat brings out the golden brown color, deepens the flavor, and crisps the texture. The toasting stage is also when much of the sweet, roasted aroma is developed. Sensors throughout the oven monitor moisture levels and color, and adjustments to temperature and conveyor speed can be made instantly to keep every batch consistent. Once the flakes are perfectly toasted, they are cooled on open-air conveyor belts to stabilize their structure. This cooling step also prepares them for the next stage that gives frosted flakes their name: sugar coating. The cooled flakes enter large, rotating tumblers known as coating drums. Here, a warm sugar syrup is sprayed onto the flakes in a fine mist. The syrup is made from refined sugar dissolved in water and heated to the right viscosity so it coats evenly without soaking the flakes. As the flakes tumble, every surface becomes covered in a thin, glossy layer. The amount of syrup applied is carefully measured to achieve the brand's signature sweetness without overpowering the cereal's natural corn flavor. After coating, the flakes pass through another drying system, often a warm air tunnel, which removes excess moisture from the syrup and crystallizes the sugar onto the flakes' surfaces. This creates the sparkling, crunchy coating that stays intact until the cereal is submerged in milk. The drying time and temperature are crucial. Too short and the sugar will be sticky. Too long and it may over-caramelize. Following coating and drying, the cereal undergoes final quality checks. It is sifted to remove broken flakes and small sugar granules. The main product stream passes through metal detectors and sometimes X-ray scanners to ensure there are no foreign materials. Samples are pulled regularly for moisture testing, color analysis, sweetness measurement, and texture evaluation. Taste panels may also evaluate random samples to confirm flavor consistency. The finished frosted flakes are then ready for packaging. The cooled flakes are conveyed to multi-head weighing machines that dispense exact portions into high-speed packaging lines. For the classic box format, an inner bag is formed from a continuous roll of food-grade plastic film, sealed at the bottom, filled with cereal, and then heat-sealed at the top. The sealed bag is automatically inserted into a pre-printed cardboard carton. The carton is glued shut, stamped with a production code for traceability, and checked by sensors to ensure it is properly sealed. From here, the cartons are conveyed to case packing machines, where they are grouped into corrugated shipping cases. These cases are sealed with adhesive tape or hot glue, labeled with batch information, and stacked onto pallets by robotic palletizers. The pallets are wrapped in stretch film for stability during transit and stored in a climate-controlled warehouse until they are shipped. Every step of the frosted flakes process takes place in a facility designed with strict food safety controls. Air handling systems keep dust and contaminants out of production zones, while stainless steel surfaces are regularly cleaned and sanitized. Automated clean-in-place systems wash the interior of cookers, dryers, and coating drums without dismantling the equipment. Workers wear protective clothing, hairnets, and gloves, and they follow hygiene protocols to prevent contamination. Once the product leaves the factory, it travels to distribution centers, then to retailers. Stock rotation at the store level ensures that consumers get fresh product with the sugar coating intact and the flakes as crisp as they were on the day they were made. Proper storage, cool, dry, and away from direct sunlight, keeps frosted flakes in peak condition for months. Behind every box of frosted flakes is a tightly controlled sequence of thermal, mechanical, and chemical transformations. From the high-pressure steam cooking that gelatinizes the starch, to the precise flaking that creates the perfect surface for sugar adhesion, to the final toasting that seals in crunch and flavor, every step is engineered for consistency. This is why a bowl of frosted flakes tastes the same, whether it was made in Michigan, Canada, or halfway across the world. The process for Reese's peanut butter cups begins with the sourcing of high-quality raw peanuts, which form the core of the filling. These peanuts are typically sourced from farms in the southeastern United States, particularly Georgia, Alabama, and the Carolinas, where the climate and soil are ideal for peanut cultivation. Once harvested, the peanuts undergo initial cleaning, shelling, and sorting at the agricultural level before being shipped in bulk to the Reese's production facility. Quality control teams inspect every shipment, screening for mold, aflatoxins, and other contaminants. Peanuts are often tested for size, moisture content, and oil composition to ensure batch consistency. Upon arrival at the factory, the peanuts are conveyed to large storage silos. From here, the process of transforming raw peanuts into the signature Reese's filling begins. The peanuts are first roasted in large-scale industrial roasters, long horizontal drums heated by indirect gas-fired flames. These rotating drums tumble the peanuts slowly, ensuring even roasting. Temperature and humidity are closely monitored throughout the roast cycle, typically maintained around 320 degrees Celsius for about 30 to 40 minutes, depending on the peanut variety and moisture content. Once roasted, the peanuts are quickly cooled using forced air cooling tunnels to halt further cooking. The skins are then removed using a process known as blanching. In mechanical blanches, peanuts are agitated against rough surfaces or rubber belts that strip away the thin, papery skins. A series of air jets and vibrating sieves separate the skins from the now blanched nuts. At this point, the peanuts are ready to be ground. In most candy factories, this process takes place in two distinct phases. First, a coarse grind reduces the peanuts into a crumbly paste. Then, a finer grinding process, often using high-speed colloid mills or stone rollers, produces a smoother texture. However, unlike creamy commercial peanut butters designed for spreads, Reese's peanut butter filling maintains a slightly gritty texture on purpose. This signature mouthfeel is the result of limiting the duration of the fine grind and carefully controlling moisture levels. The ground peanuts are blended with additional ingredients, including sugar, dextrose, salt, hydrogenated vegetable oils, and sometimes a small amount of molasses or corn syrup solids. This mixture is prepared in large industrial mixing tanks equipped with powerful paddle agitators that ensure even incorporation. The blending process is closely monitored for temperature, viscosity, and particle size distribution, which directly affect the final texture and handling characteristics. The resulting peanut butter filling is slightly crumbly, yet cohesive, designed to hold its shape when formed, but melt smoothly in the mouth. While the peanut butter filling is being prepared, another part of the factory is busy tempering chocolate. Reese's peanut butter cups use a custom milk chocolate formulation that includes cocoa solids, cocoa butter, milk fat, sugar, lecithin, and vanillin. These ingredients are pre-blended and then passed through conching machines, large vats where granite rollers continuously knead the chocolate for hours at elevated temperatures. Conching improves texture and flavor by breaking down particles and promoting the development of complex chocolate notes. After conching, the chocolate is sent to tempering units, which precisely heat and cool the chocolate in a controlled sequence to encourage the formation of stable cocoa butter crystals. Proper tempering is critical to achieving that characteristic Reese's snap and glossy finish. The chocolate must be maintained at a working temperature of approximately 88 degrees to 90 degrees for milk chocolate, depending on the formulation. Now the production line shifts into high gear with the molding and filling of each peanut butter cup. The factory floor features a long assembly line comprising conveyor belts, servo-driven depositing heads, forming stations, and robotic arms, all synchronized with computer-controlled systems. First, paper cup liners are dispensed from reels and dropped into aluminum or plastic molds that give the peanut butter cup its distinctive ridged edge. These molds are carried forward on the conveyor to the chocolate depositing station. Here, a metered amount of tempered chocolate is deposited into each mold cavity, typically via piston-driven depositors with highly accurate flow control. The molds are then gently vibrated to level the chocolate and remove any trapped air bubbles. A specialized spinning or centrifugal molding mechanism is often used to coat the sides of each liner with chocolate, forming a thin shell that will encase the peanut butter filling. Once the bottom and sides of the shell are set, often using brief passes through cooling tunnels chilled to 40 degrees F, the molds move to the filling station. At this point, the peanut butter mixture is slightly warmed to improve flowability and deposited into the center of the chocolate shell using a second set of depositors. The volume and placement are tightly controlled to ensure the filling does not breach the shell's perimeter, which would compromise product appearance and shelf life. The partially filled molds then travel through another cooling tunnel to partially firm up the filling before the final chocolate cap is added. At the next station, another measured deposit of tempered chocolate is layered on top to fully enclose the peanut butter. Vibratory and centrifugal actions again ensure that the top layer is smooth and fully seals the filling inside. After the top layer is applied, the molds pass through the final cooling tunnel. This tunnel, often more than 30 feet long, gradually lowers the product temperature to about 50 degrees to 60 degrees F. allowing the chocolate to fully crystallize and harden without cracking or bloom. At the end of the tunnel, robotic demolders invert the trays, and the solidified Reese's peanut butter cups drop gently onto another conveyor belt, which carries them to the packaging line. Packaging is a critical part of the operation, both for aesthetics and product protection. Individual cups are wrapped in printed foil or plastic film using high-speed flow wrapping machines. These machines align, wrap, heat seal, and cut the packaging material in a continuous motion at speeds of hundreds of units per minute. Sensors and vision systems verify proper alignment, seal integrity, and date coding. Multiple wrapped cups are then grouped into standard pack formats, such as 2-packs, king size, or multi-packs, using pick-and-place robots that transfer the wrapped candies into cardboard sleeves or blister packs. These are then loaded into shipping cartons by automated case packers and sent through weight check stations and metal detectors for final safety assurance. Cartons are sealed, barcoded, and palletized using robotic palletizers that arrange the boxes into stable stacks ready for shipment. The finished pallets are shrink-wrapped for transport and loaded onto refrigerated trucks, if necessary, depending on the season and destination. Distribution centers receive the pallets and coordinate the movement of Reese's products to retail chains, vending machine operators, and wholesale clubs. Shelf life is generally around 6 to 9 months, and climate-controlled storage is crucial to preventing fat bloom or flavor degradation in the chocolate. Inventory is rotated using first-in, first-out logistics to ensure product freshness. Reese's peanut butter cups may seem like a simple treat, but their production involves a complex interplay of food science, automation, engineering, and quality control. Each cup reflects countless micro-adjustments made by operators, engineers, and sensors throughout the line to maintain consistency in taste, texture, and visual appeal. Whether you're biting into a miniature, a king size, or a seasonal shape, the same rigorous standards apply across every variation. The process for Snickers begins long before a single bar is formed. It starts with the procurement of raw ingredients, each of which must meet stringent quality, flavor, and food safety standards. The peanuts used in Snickers are typically sourced from large-scale growers in the United States, particularly Georgia, Texas, and Alabama, where soil composition and climate are well suited to peanut cultivation. Once harvested, the peanuts undergo shelling, drying, and initial quality control before arriving at the candy factory in bulk loads. At the receiving dock, they're sampled and inspected for size uniformity, absence of mold or aflatoxins, and overall freshness. The peanuts are then conveyed to roasting units, large, gas-fired, rotary drum roasters that tumble and cook the nuts evenly. Roasting time and temperature are carefully controlled, often in the range of 300 degrees to 330 degrees, to ensure the development of the characteristic deep nutty flavor and golden color. As the peanuts cool on vibratory trays with forced air, their skins are loosened and removed through mechanical blanching, which typically involves abrasion and suction systems. Once the peanuts are blanched, they are screened again for foreign matter or off-grade pieces before being held in stainless steel hoppers, ready for integration into the bar. While the peanuts are being prepared, another production stream begins with the making of the nougat layer, the foundational component of every Snickers bar. Nougat is a whipped mixture, typically composed of sugar, corn syrup, egg whites, and milk powder. The sugar and corn syrup are first combined in massive stainless steel cooking kettles, where they are heated to a precise temperature, usually around 240 degrees to 250 degrees, to achieve the correct sugar structure and viscosity. This hot syrup is then transferred to continuous mixing tanks where it is combined with whipped egg whites and other dry ingredients. The blending process is highly aerated, giving the nougat its light, spongy texture. The finished nougat is deposited onto a moving conveyor belt lined with parchment or plastic film. It spreads out in a continuous sheet, generally about 1 to 2 inches thick. A series of levelers and rollers ensures uniform height and density across the sheet, which is then cooled slightly as it travels down the line. Once cooled and set, the nougat sheet proceeds to the caramel layering station. Caramel production occurs in its own dedicated section of the plant. A blend of glucose syrup, sucrose, dairy cream, and butter is cooked in open-jacketed kettles or vacuum cookers, where it is continuously stirred to avoid burning and to control the Maillard browning reactions that give caramel its signature flavor. The exact temperature and cooking duration are tightly monitored, typically between 240 degrees Celsius and 260 degrees. As soon as the desired consistency is achieved, firm enough to hold its shape but pliable enough to slice, it is poured or extruded onto the moving nougat sheet. The hot caramel forms a second, cohesive layer atop the nougat. To ensure perfect adhesion and uniform thickness, the bar sheet passes under heated rollers and through spreading nozzles that guide and adjust the caramel's distribution. The line is equipped with infrared sensors and weight check systems that continually monitor thickness and material ratios. Once the caramel has slightly cooled and stabilized, the bar sheet moves toward the peanut application zone. Roasted peanuts are sprinkled onto the warm caramel layer in a controlled shower using vibrating feed trays and metered dispensers. The combination of slightly sticky caramel and downward pressure ensures that most peanuts adhere securely. Excess or misaligned nuts are brushed away by rotating silicone paddles and collected for reuse or reprocessing. The peanuts used here are not only flavor critical, but also provide a distinctive crunch and texture contrast to the softer nougat and caramel. With all three internal layers assembled, nougat, caramel, and peanuts, the composite sheet now travels to the cutting area. Here, guillotine-style knives or rotary blade systems cut the long sheet into bar-length strips, typically around 1 inch wide. These strips are then cross-cut into individual bars, using synchronized high-speed blades. Every bar is now a complete unit, except for the chocolate coating. Before coating, the uncoated bars, often referred to as centers, pass through a quick chilling tunnel to firm up the layers and maintain bar integrity during enrobing. Once firm, the centers are deposited onto a wide enrobing belt that passes through a chocolate waterfall. This enrobing process involves a curtain of tempered milk chocolate cascading down over the moving bars. As the bars move through the curtain, chocolate coats the top and sides. A bottoming plate or chocolate pool beneath the bars coats the underside as well. The chocolate used in Snickers bars is a proprietary blend of milk chocolate ingredients, cocoa butter, cocoa liquor, sugar, milk solids, and emulsifiers. The chocolate is pre-tempered in dedicated machines that heat and cool it through specific curves to ensure stable crystal formation. This tempering is what gives Snickers its glossy finish and prevents fat bloom during storage. The temperature of the chocolate is carefully maintained between 86 degrees Celsius and 90 degrees Celsius throughout the enrobing line. As the chocolate-coated bars exit the enrober, they pass under air jets and vibrating rods known as air knives and vibrators that remove excess chocolate, improve coating uniformity, and give each bar its final shape. The still warm chocolate is soft and easily deformed, so the bars immediately enter a cooling tunnel, which gradually reduces their temperature to around 50 degrees Celsius in a staged fashion. This gradual cooling prevents cracking and ensures that the chocolate shell sets with the correct texture. Once fully cooled, the bars emerge, ready for wrapping. A high-speed automated packaging line awaits, where each bar is individually wrapped using roll-fed film wrappers. These machines synchronize bar movement with film feeding, folding, sealing, and cutting, all in one continuous operation. Heat sealers close the film edges with precision, while inline printers apply best buy dates, lot numbers, and traceability codes. The wrapped bars are then conveyed to a grouping station. Depending on the market, Snickers bars may be packed individually, bundled in twin packs, or combined into multi-unit boxes. Robotic arms sort and orient the wrapped bars, placing them into cartons that are then sealed with hot melt adhesive. The packed cartons are passed through metal detectors and weight verifiers as a final check before palletization. Palletizing robots load the boxes onto standardized pallets, wrapping them tightly in plastic film for protection and stability during shipping. From there, pallets are staged in climate-controlled distribution centers. Temperature and humidity must be carefully controlled, especially in warm climates, to preserve the bar's texture and chocolate integrity. Snickers bars are then distributed to retailers, wholesalers, and vending machine operators worldwide. Shelf life for a standard Snickers bar is generally between 9 and 12 months, assuming proper storage. Mars maintains rigorous quality control protocols, including sampling every batch for flavor consistency, structural integrity, and microbiological safety. Automated inspection systems use vision technology to detect misaligned bars, incomplete coatings, or wrapper defects, automatically removing flawed units from the line. Throughout the plant, hygiene is paramount, with clean-in-place systems for all equipment and strict allergen controls to ensure product safety. What makes Snickers particularly remarkable is how such a complex, multi-layered treat can be produced with such uniformity at an industrial scale. From raw peanuts and liquid caramel to perfectly wrapped bars stacked on pallets, every aspect of production is optimized for speed, precision, and global distribution. Millions of Snickers bars roll off the line each day, each one representing a perfected system of mass food manufacturing. It all begins with cocoa beans for Hershey's chocolate, which are the fundamental raw ingredient in all chocolate. Hershey sources its cocoa beans primarily from West Africa, countries like Côte d'Ivoire and Ghana, where the climate, soil, and traditional farming practices produce high-yield crops with desirable flavor characteristics. Once harvested, the cocoa beans are fermented in banana leaf-lined piles and dried under the sun before being packed in jute bags and shipped across the ocean to Hershey's production facilities in the United States. Upon arrival, the beans are subject to rigorous testing. Random samples from each shipment are roasted and analyzed for aroma, acidity, moisture content, and potential contaminants. Approved beans are stored in large silos, sorted by origin and quality grade. From here, the first major step in the chocolate making process begins roasting. Roasting is not just about cooking the beans, it's a chemical transformation that unlocks the complex flavors hidden within the cocoa nibs. The beans are fed into large, rotating drum roasters or continuous belt roasters and exposed to carefully controlled dry heat at temperatures between 250 degrees and 300 degrees for 20 to 30 minutes. This Maillard reaction develops the chocolate flavor while drying the beans further and loosening the outer shells. The duration and temperature of the roast are adjusted depending on the origin and size of the beans, with constant airflow and humidity control. After roasting, the beans are cooled and sent through cracking machines that break them open, separating the brittle outer shells from the inner nibs. The broken shell pieces are removed through winnowing, a process that uses airflow to lift away the lighter shells, leaving behind clean cocoa nibs. These nibs are the essence of chocolate, rich in cocoa solids and cocoa butter. The nibs are then ground into a thick, gritty paste called chocolate liquor, not to be confused with alcohol. This step is performed in heavy-duty grinding mills, such as stone refiners or steel disc mills, which apply intense pressure and friction. As the nibs break down, their fat melts, turning the mass into a thick, flowing fluid. At this point, the chocolate liquor is still unrefined, with a coarse texture and bitter flavor. For milk chocolate, Hershey adds a blend of sugar, milk ingredients, and sometimes vanilla and lecithin to the chocolate liquor. One of the defining features of Hershey's milk chocolate is its use of fresh fluid milk that is processed in-house. Unlike European chocolates that often use powdered or condensed milk, Hershey pioneered a method of processing fresh milk into milk crumb, a dehydrated mixture of milk solids and sugar, using vacuum cooking and drum drying techniques. This milk crumb, with its slightly tangy cooked flavor, contributes to the uniquely Hershey taste. The chocolate liquor, milk crumb, and sugar are blended in large stainless steel mixing tanks, forming a uniform paste. At this stage, the mixture is still coarse and gritty, unsuitable for final chocolate texture. It must be refined. The refining process involves passing the chocolate mass through a series of roller mills, typically 5-roll refiners that reduce the particle size of the solids to less than 30 microns. The goal is to achieve a silky smooth mouthfeel without any noticeable graininess. Once refined, the chocolate enters the conching phase, one of the most critical steps in flavor development. Conching is a process of continuous mixing, aerating, and heating the chocolate over many hours to improve its taste and texture. Hershey's uses a combination of traditional longitudinal conches and modern rotary conches that knead the chocolate at controlled temperatures, typically between 120 degF and 180 degF. This process helps evaporate undesirable volatile acids, mellow bitter notes, and fully integrate the milk and cocoa flavors. The viscosity and aroma are fine-tuned during this stage through mechanical shearing and time adjustments. Following conching, the chocolate undergoes tempering, a heat treatment process that ensures the final product has a smooth, glossy finish and a crisp snap when broken. Cocoa butter can crystallize in several forms, but only one, known as Form 5, gives chocolate its ideal physical properties. Tempering involves heating the chocolate to about 115 degrees, then cooling it down to around 80 degrees, and finally reheating it slightly to about 88 degrees to promote the formation of stable crystals. This carefully controlled cycle is performed in continuous tempering machines, which maintain consistent temperatures and flow rates. Tempered chocolate is now ready for molding. Hershey's uses high-speed molding lines where liquid chocolate is deposited into polycarbonate molds in precise weights. The molds are vibrated to remove air bubbles and ensure even distribution. For classic bars like the Hershey's Milk Chocolate Bar, the molds are designed with the familiar rectangular break-apart sections embossed with the Hershey name. Once filled, the molds travel through long refrigerated cooling tunnels where the chocolate solidifies into its final form. As the bars cool, they are monitored by temperature sensors and mechanical feelers to ensure proper release. When fully set, the bars are automatically ejected from the molds and conveyed to the wrapping station. Modern wrapping equipment is synchronized with bar output and uses roll-fed film that is printed with the Hershey's branding, ingredients, and expiration codes. Wrappers are folded and sealed using rotary crimpers, and a barcode is applied for tracking. Wrapped bars are then grouped into cartons or display trays using robotic pick-and-place systems and conveyed to the end-of-line packaging area. Here, cases are formed, filled, and sealed before being palletized by automated arms. Each pallet is shrink-wrapped and scanned into inventory, ready for transport to distribution centers across the country and around the world. Throughout the entire process, quality control is a constant presence. Samples are pulled from every batch for testing. Sensory panels evaluate flavor and aroma, while lab technicians measure moisture content, fat percentage, and microbial levels. Machine vision systems inspect each bar for dimensional accuracy and surface defects. Metal detectors and X-ray machines scan for foreign objects, while thermal imaging cameras check for temperature compliance at various stages. Behind the scenes, Hershey's factories are tightly integrated with computerized control systems that track every ingredient, process parameter, and output metric in real time. From ingredient blending to chocolate tempering and bar wrapping, programmable logic controllers and supervisory control and data acquisition systems coordinate the hundreds of motors, valves, conveyors, and sensors that make up the line. These systems not only maximize efficiency and reduce downtime, but also ensure that each bar tastes the same as the one before it. Once packaged and palletized, Hershey's bars enter the post-production logistics chain. Distribution centers maintain climate-controlled storage to preserve chocolate integrity. Trucks are loaded according to first-in, first-out scheduling, and GPS tracking systems ensure timely delivery to retailers, vending machine operators, and wholesalers. Chocolate bars are especially sensitive to heat and humidity, so strict environmental controls are observed throughout transportation and warehousing to prevent melting or bloom. Interestingly, the Hershey flavor that many Americans recognize and even associate with nostalgia is not accidental. It's the result of deliberate formulation choices, particularly in how milk is treated during production. Some analysts believe the signature, slightly sour or tangy flavor found in Hershey's milk chocolate comes from the breakdown of milk fats into butyric acid during controlled lipolysis, an effect that differentiates Hershey's from creamier European chocolates. This flavor profile has become a cultural benchmark in the United States, deeply woven into American food identity. Despite decades of innovation and scaling up, the heart of Hershey's chocolate production still echoes the vision of its founder: to make high-quality milk chocolate affordable and accessible to everyone. With more than a century of history and tens of millions of bars produced annually, Hershey's remains a pioneer in automated food manufacturing, exemplifying the blend of tradition, precision engineering, and industrial food science. From bean to bar, the production of Hershey's chocolate is a story of transformation, driven by technology but grounded in flavor. To create the world's most beloved hazelnut and cocoa spread, the manufacturing facilities are equipped with advanced machinery, precision-engineered systems, and rigorous quality controls. Each step in the process is optimized for efficiency, consistency, and the highest standards of food safety. In this detailed breakdown, we'll explore how Nutella is made inside a modern factory, from the raw materials to the final product, with a close look at the construction, operation, and technical aspects of the factory's systems and machinery. The process begins with the sourcing of raw ingredients, including hazelnuts, sugar, cocoa powder, palm oil, skim milk powder, and vanillin. These ingredients are delivered to Nutella factories in massive quantities, requiring large-scale handling infrastructure. Hazelnuts, one of the key components of Nutella, are often sourced from Turkey and Italy, two of the largest hazelnut producers in the world. Upon arrival at the factory, hazelnuts are stored in enormous silos or temperature-controlled storage rooms to maintain their freshness. The silos are made of food-grade stainless steel and designed to protect the nuts from humidity and contamination, while allowing for precise dispensing into the production line. The first step in processing the hazelnuts is cleaning. Hazelnuts arrive in bulk shipments, often mixed with debris such as shells, stems, and dirt. To address this, the factory uses a series of cleaning systems that include vibrating screens, air classifiers, and magnetic separators. The vibrating screens shake the nuts to separate them from larger debris, while the air classifiers blow away lightweight impurities like husks and dust. Magnetic separators are also used to detect and remove any metallic particles that might have entered the shipment during harvesting or transport. Once cleaned, the hazelnuts undergo visual inspection using high-speed optical sorting machines equipped with cameras and sensors. These machines identify and remove any defective hazelnuts, such as those with discoloration, cracks, or signs of mold. After cleaning, the hazelnuts move to the roasting stage. Roasting is a crucial step in developing the rich, nutty flavor that characterizes Nutella. In the factory, this is achieved using massive industrial roasting ovens. These ovens are designed with rotating drums or conveyor belts to ensure even roasting. The temperature is carefully controlled, typically ranging between 280 and 320 degrees Fahrenheit, depending on the size and moisture content of the hazelnuts. Sensors monitor the temperature and time to ensure consistency, as over-roasting can lead to bitterness, while under-roasting can result in a lack of flavor. The entire roasting process is automated, and the equipment is designed for continuous operation to handle the high volume of hazelnuts required for production. Once roasted, the hazelnuts are transferred to grinding machines. These machines are equipped with heavy-duty stainless steel blades and rollers that crush the nuts into a fine paste. The grinding process occurs in multiple stages, with each stage further reducing the particle size of the hazelnut paste. In the initial stage, the nuts are coarsely ground into a chunky paste. In the subsequent stages, the paste is refined into a smooth consistency, with particle sizes measuring less than 30 microns. This ultra-fine grinding is essential for achieving Nutella's creamy texture. The equipment used in this process, such as colloid mills and ball mills, is highly specialized and designed to operate under high pressure and at precise speeds. The resulting hazelnut paste is collected in large stainless steel tanks, where it is stored at a controlled temperature to preserve its flavor and consistency. While the hazelnut paste is being prepared, the other ingredients are processed in parallel. Sugar, which provides sweetness to Nutella, is delivered to the factory in bulk containers or tankers. Upon arrival, the sugar is unloaded into silos, equipped with pneumatic conveying systems. These systems use air pressure to transport the sugar from the silos to the milling area, where it is ground into a fine powder. Industrial sugar mills are used for this purpose, and the grinding process ensures that the sugar particles are small enough to dissolve uniformly in the mixture. The factory also incorporates sieving systems to filter out any impurities or oversized sugar particles before they proceed to the blending stage. Cocoa powder, another key ingredient, undergoes a similar process. The cocoa powder is stored in sealed silos to protect it from moisture and contamination. Before being added to the Nutella mixture, the cocoa powder is sifted through vibrating screens to break up clumps and ensure a fine, even consistency. This step is crucial for achieving the smooth texture of the final product, as any clumps could create inconsistencies during blending. Palm oil, which gives Nutella its creamy consistency and prevents separation, is stored in large, temperature-controlled tanks. These tanks are equipped with heating elements to keep the oil in a liquid state, as palm oil tends to solidify at room temperature. The oil is pumped through insulated pipes to the mixing area, where it is carefully measured and added to the blend. The precise control of temperature and flow rate is essential to ensure that the oil integrates smoothly with the other ingredients. Skim milk powder, which adds a subtle dairy flavor and contributes to the creamy texture of Nutella, is stored in sealed containers or silos to prevent exposure to air and moisture. Before being used, the milk powder is sifted and screened to remove any lumps. Factories use advanced pneumatic conveying systems to transport the milk powder from the storage silos to the mixing area, ensuring that the ingredient is handled efficiently and hygienically. The blending process is the heart of Nutella's production, where all the prepared ingredients come together to form the final product. The blending tanks used in Nutella factories are massive, often with capacities of several thousand gallons. These tanks are equipped with high-speed agitators and temperature control systems. The hazelnut paste, sugar powder, cocoa powder, skim milk powder, palm oil, and vanillin are added to the tank in precise proportions, which are controlled by computerized dosing systems. These systems are programmed to weigh and dispense each ingredient accurately, ensuring consistency across batches. During blending, the mixture is heated slightly to help the ingredients combine more effectively. The temperature is carefully monitored, as excessive heat could alter the flavor and texture of the product. The blending tanks are designed to ensure even mixing, with agitators that create a vortex to incorporate all the ingredients thoroughly. The result is a homogeneous mixture with a smooth, creamy consistency. Once the blending process is complete, the mixture undergoes a refining stage. Refining is a critical step that ensures the final product is free of any graininess. The refining process takes place in multi-stage roller mills, which are equipped with heavy-duty steel rollers. These rollers apply immense pressure to the mixture, reducing the particle size of any remaining solids to less than 20 microns. This process not only enhances the texture of Nutella, but also improves its spreadability. The roller mills are fitted with precision sensors that monitor the pressure and temperature during refining, ensuring optimal performance. After refining, the mixture is transferred to the conching stage. Conching is a process borrowed from chocolate manufacturing and involves agitating the mixture in large, heated tanks for several hours. This process helps to further smooth the texture and enhance the flavor of the spread by allowing volatile compounds to evaporate and by evenly distributing the fats and solids. The conching tanks are equipped with paddles or rollers that knead the mixture continuously. The temperature and duration of conching are carefully controlled, as overconching could negatively affect the spread's consistency. The finished Nutella is then pumped into holding tanks, where it is kept at a controlled temperature until it is ready for packaging. These tanks are equipped with agitators to prevent separation and maintain the spread's uniformity. Before the Nutella is packaged, it undergoes a final round of quality control. Samples from each batch are tested for flavor, texture, color, and viscosity. The factory uses advanced laboratory equipment such as viscometers and spectrophotometers to ensure that the product meets the company's stringent standards. Any deviations from the desired specifications are identified and corrected before the product proceeds to the packaging stage. Packaging is the final step in Nutella's production process, and it is carried out with the same level of precision and efficiency as the earlier stages. The spread is pumped from the holding tanks into automated filling machines, which dispense precise amounts of Nutella into jars. The filling machines are equipped with high-speed nozzles that can fill hundreds of jars per minute. Each jar is made from food-grade plastic or glass and arrives at the factory pre-sterilized to ensure hygiene. The jars are sealed with tamper-proof lids, which are applied and tightened using automated capping machines. Once the jars are sealed, they are conveyed to labeling stations, where Nutella's iconic branding is applied. The labels include important information such as the lot number, production date, and expiration date, which are printed using high-speed inkjet or laser printers. After labeling, the jars are inspected by vision systems that check for defects such as misaligned labels or damaged seals. Any defective jars are automatically removed from the production line. The jars are then packed into cardboard cartons using robotic packing systems. These systems are programmed to arrange the jars in specific configurations to maximize space and protect the jars during transportation. The cartons are sealed and stacked onto pallets using robotic palletizers. The pallets are then wrapped in plastic film for stability and loaded onto trucks or shipping containers for distribution. The entire packaging process is designed for high efficiency, with minimal manual intervention and maximum output. Throughout the factory, automation plays a key role in maintaining efficiency and consistency. Programmable logic controllers and supervisory control and data acquisition systems are used to monitor and control every aspect of the production process. These systems provide real-time data on parameters such as temperature, pressure, and flow rates, allowing operators to make adjustments as needed. The factory is also equipped with advanced robotics and machinery that ensure smooth operation, from ingredient handling to final packaging. Hygiene and safety are top priorities in Nutella factories. Production areas are constructed with food-grade stainless steel surfaces and epoxy-coated floors that are easy to clean and sanitize. Air filtration systems maintain a clean environment by preventing airborne contaminants from entering critical zones. Employees follow strict hygiene protocols, including wearing protective clothing and washing their hands regularly. The factory is regularly inspected to ensure compliance with international food safety standards, guaranteeing that every jar of Nutella is safe for consumption. This intricate, highly automated process ensures that Nutella is consistently smooth, flavorful, and delicious, meeting the high expectations of its millions of fans worldwide. Every step, from the handling of raw ingredients to the final packaging, is a testament to the engineering and precision that go into creating this beloved spread. The result is a product that continues to delight consumers, one jar at a time. Peanut butter, a staple spread beloved worldwide for its creamy or crunchy texture, requires a sophisticated and highly organized manufacturing process to meet the demand for consistent quality and flavor. Behind every jar of peanut butter is an intricate factory process that starts with the raw peanuts and ends with precisely packaged jars ready for distribution. Let's take an in-depth look at the factory production process, exploring the machines, systems, and engineering techniques that make it all possible. The process begins with the sourcing of raw peanuts. These peanuts are typically grown in countries like the United States, China, India, and Argentina, which are among the largest producers of peanuts globally. Peanuts are harvested in vast quantities, cleaned and dried at their source before being shipped to peanut butter manufacturing facilities. Factories require a consistent supply of high-quality peanuts, and to ensure that the raw peanuts are often tested upon arrival for size, moisture content, and overall quality. This ensures only the best peanuts are used for processing. Upon arrival at the factory, peanuts are stored in massive silos or bins designed specifically for food products. These silos are constructed from food-grade stainless steel or coated steel to prevent contamination and ensure proper hygiene. Inside the silos, the peanuts are protected from moisture, pests, and temperature fluctuations. These storage systems are equipped with conveyor systems that efficiently transfer peanuts from the silos to the initial cleaning and processing stages. The first step in processing peanuts is cleaning. Even though peanuts are partially cleaned at their source, factories implement a rigorous cleaning process to ensure no foreign materials or impurities remain. Vibrating screens are used to remove debris such as dirt, stones, and small sticks. Air classifiers blow air through the peanuts to remove lighter debris such as peanut skins or husks. Magnets are also employed to extract any metallic impurities. Optical sorting machines equipped with cameras and sensors scan each peanut as it moves along a conveyor belt, automatically removing any defective peanuts, including those with discoloration, mold, or deformities. After the cleaning process, the peanuts proceed to the roasting stage. Roasting is a critical step in peanut butter production, as it develops the rich, nutty flavor that defines the final product. Factories use industrial roasting ovens to roast the peanuts at controlled temperatures. These ovens come in two main types: batch roasters and continuous roasters. Batch roasters are used for smaller production lines, while continuous roasters, which use conveyor belts to move peanuts through a heated chamber, are used for larger scale operations. The temperature in these roasters typically ranges from 300 to 350 degrees Fahrenheit. The roasting process is closely monitored with temperature sensors and automated control systems to ensure the peanuts are roasted evenly. If some peanuts are over-roasted, they can turn bitter, while under-roasted peanuts may lack flavor. The level of roasting can also be adjusted depending on whether the final peanut butter will have a mild or more robust taste. Once roasted, the peanuts are cooled to stop the cooking process. Cooling is achieved by passing the roasted peanuts through chambers with powerful fans or cool air blowers. This step is crucial because it prevents the peanuts from continuing to cook, which could lead to inconsistencies in flavor. Some factories also use a water spray system to rapidly cool the peanuts, though this is less common as it can add moisture to the product. The cooling systems are designed to operate continuously to keep pace with the output of the roasting ovens. With the peanuts roasted and cooled, the next step is to remove their skins and separate the kernels. Skin removal is done using blanching machines. These machines have rotating drums or abrasive rollers that rub the peanuts, causing the thin outer skin to flake off. Some systems use steam blanching, where the peanuts are exposed to high-pressure steam to loosen the skins before mechanical removal. After blanching, the peanuts pass through air classifiers that blow away the loose skins, leaving behind clean peanut kernels. Factories also use gravity separators to sort peanuts by size and density, ensuring that only uniform peanuts proceed to the grinding stage. Before grinding, the peanuts are inspected again for quality. This is done using high-speed optical sorters that ensure any remaining defective peanuts are removed. Factories often have automated weighing and proportioning systems at this stage to determine the exact amount of peanuts needed for each batch. This level of precision is crucial for maintaining consistency in the flavor and texture of the peanut butter. The grinding process is the heart of peanut butter production. The roasted peanuts are fed into industrial grinders, where they are crushed into a fine paste. This process happens in multiple stages, beginning with coarse grinding and followed by finer grinding. The equipment used for this includes hammer mills and roller mills, which are specifically designed to reduce the peanuts into small, uniform particles. In many factories, the particle size is reduced to less than 20 microns, which is smaller than the diameter of a human hair. Achieving such a fine consistency is essential for the creamy texture that many consumers expect from peanut butter. For crunchy peanut butter, the process is slightly different. In these cases, a portion of the peanuts is coarsely ground and set aside before the final blending stage. These larger peanut pieces are later mixed into the smooth paste to create the characteristic crunchy texture. To prevent the peanut butter from separating, stabilizers such as hydrogenated vegetable oils or palm oil are added during the grinding process. These oils help bind the natural peanut oils to the solid peanut particles, ensuring a smooth and stable product that doesn't separate in the jar. Salt and sugar are also added at this stage to enhance the flavor of the peanut butter. Factories use precision dosing systems to measure and add these ingredients in exact proportions, ensuring every batch has the same taste. After grinding, the peanut butter is sent through a mixing stage, where it is further blended in large stainless steel tanks equipped with high-speed agitators. This stage ensures that the stabilizers, salt, and sugar are evenly distributed throughout the peanut butter. These tanks are often heated slightly to keep the peanut butter at the right consistency for mixing. The temperature is carefully controlled, as overheating can alter the flavor or texture of the peanut butter. Once the mixing is complete, the peanut butter undergoes quality control checks. Samples from each batch are tested in an on-site laboratory for flavor, texture, and consistency. Advanced instruments, such as viscometers, are used to measure the viscosity of the peanut butter, ensuring it meets the desired standards. Factories also use particle size analyzers to confirm that the peanut butter's texture is smooth and uniform. These quality checks are critical, as even slight variations can impact the final product's appeal to consumers. The final step in the manufacturing process is packaging. The peanut butter is pumped from the mixing tanks to filling machines, where it is dispensed into jars. These filling machines are capable of handling thousands of jars per hour, ensuring high efficiency. The jars, typically made of food-grade plastic or glass, arrive at the factory pre-cleaned and are sterilized again before filling. The filling nozzles are designed to dispense precise amounts of peanut butter into each jar, ensuring uniform weight and volume. Once the jars are filled, they move to the capping machines, where tamper-proof lids are applied and tightened. After capping, the jars are conveyed to labeling machines, which apply the brand's signature labels, along with lot numbers and expiration dates for traceability. Vision systems inspect each jar to ensure that the labels are correctly applied and that there are no defects in the seals or packaging. The jars are then packed into cardboard boxes using robotic packing systems. These robots are programmed to arrange the jars in specific configurations to optimize space and protect the jars during transportation. The boxes are sealed and stacked onto pallets using automated palletizing systems. Finally, the pallets are wrapped in plastic film for stability and loaded onto trucks or shipping containers for distribution. Throughout the entire production process, automation plays a vital role in maintaining efficiency and consistency. Factories are equipped with programmable logic controllers, PLCs, and supervisory control and data acquisition, SCADA systems, that monitor and control every aspect of production. These systems provide real-time data on parameters such as temperature, pressure, and flow rates, allowing operators to make adjustments as needed. Robotic systems handle many tasks, from sorting and cleaning peanuts to packaging the final product, reducing the need for manual labor and ensuring precision. Hygiene and safety are also top priorities in peanut butter factories. The production areas are constructed with food-grade stainless steel surfaces and epoxy-coated floors that are easy to clean and sanitize. Positive air pressure systems prevent airborne contaminants from entering critical zones, while strict hygiene protocols ensure that employees maintain cleanliness throughout the production process. The entire facility is regularly inspected to comply with international food safety standards, ensuring that every jar of peanut butter is safe for consumption. Peanut butter production is a complex and highly technical process that relies on advanced machinery, precise engineering, and rigorous quality control. From the cleaning and roasting of peanuts to the grinding, mixing, and packaging of the final product, every step is designed to create a spread that is smooth, flavorful, and consistent. Factories operate with remarkable efficiency, producing thousands of jars per day to meet the global demand for this versatile and beloved product. Strawberry jam production is a fascinating and highly engineered process that combines precision machinery with time-tested techniques to create a smooth, fruity spread. At the core of this process are high-quality strawberries, sugar, pectin, and citric acid, all carefully handled and processed to achieve the perfect consistency and flavor. Inside a modern jam factory, every step is optimized for efficiency, consistency, and food safety. The process begins with the selection and delivery of fresh or frozen strawberries. Factories typically source strawberries from local farms or large-scale suppliers. Frozen strawberries are often preferred for large-scale production because they are preserved at peak ripeness, ensuring consistent flavor year-round. The strawberries arrive in bulk containers and are stored in cold rooms or freezers to maintain their quality until processing begins. Before entering the production line, the fruit undergoes a thorough cleaning process. This includes washing the strawberries in large tanks filled with filtered water, where gentle agitation removes dirt, debris, and any residual pesticides. Once cleaned, the strawberries pass through optical sorting machines. These machines use cameras and sensors to identify and remove defective or discolored fruit. Advanced systems can even detect minute imperfections, ensuring that only the highest quality strawberries make it into the jam. After sorting, the strawberries are sent to cutting or mashing machines, depending on the desired jam texture. For chunkier jams, strawberries are coarsely chopped, while for smooth spreads, they are mashed or pureed into a uniform consistency. The fruit then enters large stainless steel cooking kettles or continuous cooking systems. In these vessels, the strawberries are combined with sugar, which not only sweetens the jam, but also acts as a natural preservative. The sugar is added using automated dosing systems that measure precise quantities to ensure consistent flavor. Pectin, a natural thickening agent derived from fruit, is added to help the jam set. Citric acid is also incorporated to balance the sweetness and enhance the fruit's natural flavor. The mixture is slowly heated, with temperatures reaching up to 220 degrees Fahrenheit to activate the pectin and achieve the ideal gel-like consistency. During cooking, the jam undergoes constant agitation to prevent scorching and ensure even heating. Steam-jacketed kettles or vacuum cookers are often used, as they allow for rapid and uniform heating. Modern vacuum systems are particularly advantageous because they enable cooking at lower temperatures, preserving the fresh flavor and bright color of the strawberries. Throughout the cooking process, sensors monitor the temperature, pH levels, and viscosity of the jam, ensuring that the final product meets strict quality standards. Once the jam reaches the desired consistency, it is pumped through a series of filters to remove any seeds or large pieces if a smoother texture is desired. The finished jam is then transferred to filling machines. These machines dispense precise amounts of jam into sterilized glass jars or plastic containers. The jars are immediately sealed with tamper-proof lids to maintain freshness and prevent contamination. After sealing, the jars are passed through pasteurization tunnels, where they are briefly heated to destroy any remaining microorganisms. Finally, the jars are labeled, inspected, and packed into cartons using robotic packaging systems. The entire process is highly automated, ensuring efficiency and consistent quality, from the arrival of fresh strawberries to the delivery of jars to store shelves. This seamless blend of traditional cooking techniques and advanced technology ensures that every jar of strawberry jam is rich in flavor, perfectly textured, and safe for consumers to enjoy. It all begins, unsurprisingly, with flour. Krispy Kreme uses a proprietary blend of enriched wheat flour, one formulated specifically for its lightness, protein balance, and ability to yield that signature fluffy bite. The flour is sourced from select mills that maintain tight quality control standards, ensuring the particle size, protein content, and gluten strength all fall within strict tolerances. Once delivered to the facility, the flour is stored in stainless steel silos under controlled temperature and humidity, preventing clumping and spoilage. Next, there's yeast, the biological engine behind the dough's rise. Krispy Kreme uses a commercial strain of baker's yeast known for its rapid activation, consistent fermentation profile, and neutral flavor. The yeast is usually delivered in refrigerated blocks or vacuum-sealed pouches to ensure maximum viability. Alongside the yeast, the other raw ingredients include non-fat dry milk powder, high-stability vegetable shortening, dextrose, salt, and water. Each of these ingredients plays a crucial role in shaping the final taste and texture of the donut. The shortening provides mouthfeel and moisture retention, while the dry milk lends a creamy undertone and enhances browning during frying. In the mixing phase, the ingredients are loaded into a spiral or planetary industrial mixer. The water is typically warmed to around 95 to 105 degrees Celsius before being introduced to activate the yeast. The mixer operates on a timed cycle, first gently combining the dry and wet components, then increasing speed to develop gluten and build dough structure. The dough is mixed until it achieves a smooth, elastic consistency with careful monitoring of temperature and hydration levels. If the dough becomes too warm, it risks overproofing, too cold, and fermentation is delayed. Sensors in the mixing bowl monitor the dough's internal temperature, moisture content, and even CO2 output to ensure consistency. Once the dough is formed, it enters the bulk fermentation phase. Giant stainless steel troughs, called dough rests, hold the dough as it ferments for the first time. During this period, the yeast metabolizes sugars and starches, producing carbon dioxide and ethanol. This expands the dough and begins developing its light, spongy structure. Krispy Kreme controls this step precisely, maintaining a temperature of around 80 degrees and 85% relative humidity in the proofing room. The dough rests here for approximately 30 to 40 minutes, depending on the batch size and ambient conditions. After bulk fermentation, the dough is transferred to a sheeting system. This is where things start to get visually impressive. The dough is rolled and flattened by calibrated rollers until it reaches a uniform thickness, typically between 10 to 12 millimeters. From here, it enters the cutting stage. A rotary die cutter stamps out perfect donut rings and holes in a continuous, automated process. The cutting dies are precision machined from stainless steel to ensure sharp, clean cuts and minimal dough waste. Any scrap dough is immediately collected by conveyors and reintroduced into the mixing system for reuse. Each donut ring now travels along a conveyor to the second proofing chamber, essentially a gigantic, climate-controlled cabinet lined with slow-moving racks. Inside, the donuts undergo their final proof, where they double in size due to continued yeast activity. The environment here is tightly regulated, around 90 degrees here and nearly 85% humidity. This proofing process typically lasts 30 minutes, but sensors embedded in the chamber walls adjust for ambient shifts in temperature or humidity, ensuring each donut achieves the perfect rise. Now comes one of the most mesmerizing parts of the process, the fry line. The fully proofed donuts are gently deposited into a continuous flow fryer using an overhead lifting mechanism that preserves their delicate structure. The frying oil, usually a high-stability palm or soybean blend, is maintained at a precise temperature of approximately 365 degrees. Each donut floats along the surface, first frying one side, then automatically flipping at the midpoint using a mechanical turner. This results in the even golden brown exterior Krispy Kreme is known for, with a pale proof line around the center indicating proper fermentation. The frying process takes just under a minute per side, and the timing is crucial. Over-frying results in a dense, oily product. Under-frying leaves it doughy and structurally unsound. Oil filtration systems continuously clean and circulate the frying oil, removing carbonized particles and extending the oil's life while maintaining food safety. Once the donuts exit the fryer, they move onto a draining conveyor where excess oil drips away. The donuts are now fully cooked, but they're still bare until they pass through the glaze waterfall. This is the stage most visitors at Krispy Kreme stores eagerly watch through the viewing window. The glaze itself is a proprietary blend of confectioner's sugar, water, and stabilizers, mixed in large heated vats to maintain fluidity. It's heated to a precise temperature to ensure it flows evenly over the donuts without soaking them. As the donuts travel beneath the waterfall, a curtain of glaze coats their entire surface in one smooth motion. The donuts continue to move along the belt for several feet to allow the glaze to set. During this time, cooling fans blow across the surface to speed up the crystallization process, giving the glaze its characteristic sheen and snap. At this stage, the original glazed donuts are complete, but not all donuts stop here. Many are diverted down alternate lines for filling, topping, or decoration. Filled varieties like custard, jelly, or cream-filled donuts are processed using pneumatic injection stations. The donuts are gripped and punctured automatically, and then a precise quantity of filling is injected into each center using calibrated nozzles. Topping lines include various enrobing stations for chocolate dips, icing drizzles, and even cookie crumb coatings, depending on the product line. Once decorated, the donuts pass through a final quality control checkpoint. Here, high-speed cameras, sensors, and human inspectors work in tandem to identify deformities, glaze coverage issues, or structural flaws. Any donut that doesn't meet the company's stringent standards is diverted and discarded or sent for animal feed, depending on local regulations. Now comes the packaging process. Original glazed donuts are usually arranged by robotic arms into branded trays or boxes, depending on the sales channel, whether destined for in-store display, grocery retail, or food service distribution. Boxes are barcoded, date-stamped, and sealed automatically. For freshness, Krispy Kreme relies on just-in-time manufacturing. Many facilities bake and ship multiple times per day, with some outlets even co-located within the production plant itself to reduce handling and delay. For external distribution, the boxed donuts are loaded into climate-controlled trucks equipped with racking systems that prevent damage during transit. These trucks make scheduled routes to retail locations, grocery partners, and kiosk outlets, often arriving just hours after the donuts were made. Once on site, employees stock the shelves or display racks, ensuring the donuts are sold within their optimal freshness window, typically less than 24 hours. Meanwhile, any donuts not sold by the end of the day are generally removed to preserve Krispy Kreme's reputation for freshness. In some regions, unsold inventory is donated to food banks or repurposed, while others adhere to strict disposal policies. Throughout this entire process, automation and precision engineering play a central role. From programmable logic controllers managing the mixing and proofing cycles, to machine vision systems inspecting glaze coverage, every step is optimized for consistency, safety, and speed. The machinery involved is custom designed, often proprietary, and requires teams of trained technicians to maintain. Clean-in-place systems are installed throughout the facility to sanitize pipes, mixers, glaze troughs, and conveyors between production runs. This minimizes downtime while ensuring compliance with food safety regulations. Every aspect, from microbial swab testing to allergen control and traceability, is monitored via centralized software platforms, which can track each batch of donuts from flour silo to store shelf. The story of every M&M starts with one essential component: chocolate. The heart of a standard M&M is a solid drop of milk chocolate, though other varieties, like peanut, almond, crispy, pretzel, or peanut butter, feature different cores. But regardless of the variety, the production begins in the chocolate refining department, where raw ingredients such as cocoa liquor, cocoa butter, sugar, and milk solids are blended to make a smooth, consistent chocolate base. The chocolate used in M&Ms is tailored for firmness and melt resistance, specifically engineered to maintain its structure during the coating process. Large stainless steel tanks are used to melt and hold the chocolate at controlled temperatures. Automated valves and mixers regulate temperature, viscosity, and flow characteristics. Chocolate destined for M&M production must be carefully refined to reduce particle size, usually to around 20 microns. This is done in multiple stages using equipment like ball mills, roller refiners, and conchas. These machines apply friction, pressure, and shear force to break down the solid particles until the chocolate achieves its desired mouthfeel. Once refined, the chocolate is pumped to depositors, automated nozzles that precisely dispense the liquid chocolate into molds or droplet-forming equipment. For the classic M&Ms, the chocolate is dropped onto a cool, rotating belt in small, round portions, forming button-shaped discs. These droplets are cooled rapidly using chilled air tunnels to harden them before further processing. The cooled chocolate centers are then collected and sent to the coating drums. These are large rotating pans, sometimes referred to as dragees pans or coating kettles, where the hard candy shell is gradually built around the chocolate core. This is the heart of the M&M production process and one of the most visually striking steps in the factory. The coating process is a slow and incremental buildup, achieved by spraying a fine mist of sugar syrup onto the tumbling chocolate centers, then drying and hardening that layer before repeating the cycle. Each coating drum can hold hundreds of thousands of chocolate centers at once. As the drum rotates, a fine spray of syrup, consisting mainly of sugar and water with optional corn syrup, is applied in short bursts. Warm air is then blown into the drum to dry the layer, allowing the sugar to crystallize into a thin, hard shell. This cycle is repeated dozens of times, each time adding a microscopically thin layer to build up the final shell thickness. Over time, this layering transforms the centers from soft chocolate buttons to perfectly round, hard-shelled candies. During this stage, technicians monitor coating uniformity, size consistency, and drying times using high-speed cameras and inline sensors. If the temperature or humidity in the coating room deviates too far from spec, it can ruin an entire batch, leading to shell cracking or poor adhesion. Once the desired shell thickness is achieved, the M&Ms are polished to give them their signature shine. This is done by adding polishing agents, such as carnauba wax or beeswax, to the coating drum in very small amounts. These natural food-grade waxes help create a glossy finish that not only enhances visual appeal, but also helps prevent sticking and moisture absorption during storage. The polishing phase takes less time than coating, but must be precisely timed to avoid overwaxing, which can result in a greasy or smeared appearance. The next step is color application, which may seem simple, but is, in fact, a carefully controlled phase. M&Ms come in a variety of colors, typically red, orange, yellow, green, blue, and brown. The color coding is applied using a sugar-based dye solution, sprayed in another round of layering inside rotating pans. Each batch is divided according to how many of each color are required. Food-grade colorants are mixed with water and a binding agent to ensure even adherence to the existing shell. After the colorant is applied, warm air is used to dry the layer, and another wax polish may be added to lock in the color and maintain shine. The factory uses precise batch tracking and automated scheduling software to ensure the correct number of each color is produced. For example, if red accounts for 20% of a standard bag's color distribution, the system ensures exactly that percentage is created during the run. This attention to detail keeps the consumer experience consistent across bags, boxes, and geographic regions. After color coding, the candies proceed to the printing station, where the iconic M is stamped on each piece. This is accomplished using high-speed, food-safe ink printers. The M&Ms are gently vibrated into a single layer on a moving conveyor belt that aligns them properly for stamping. The white edible ink is applied using a flexographic or offset stamping mechanism that imprints the M logo without damaging the candy surface. To ensure accuracy, machine vision systems monitor the printing in real time, checking for clarity, alignment, and completeness. Any candies that are misprinted or blank may be removed by pneumatic air jets and diverted for recycling or reprocessing. Now the M&Ms are ready for packaging. This phase of production involves a combination of robotics, weight-checking systems, and packaging machinery that operates at astonishing speeds. The candies are directed into vertical form-fill-seal machines or horizontal flow wrappers, depending on the packaging format. Multi-head weighers dispense precise quantities of M&Ms into each bag or pouch, ensuring weight compliance to legal standards. The packaging film is heat-sealed to form a tamper-evident, airtight barrier that preserves freshness and extends shelf life. For bulk formats, such as large tubs, party-sized bags, or vending packs, the process is slightly different but still highly automated. The machines are programmed to handle various product sizes, materials, and pack types without compromising accuracy. Barcodes, expiration dates, and lot numbers are printed onto each package to allow for traceability. Once packaged, the products are conveyed to case packing robots, which group them into cartons or boxes for shipping. These cases are then sealed, palletized by robotic arms, and shrink-wrapped for transport. Pallets are stored temporarily in climate-controlled warehouses before being loaded onto distribution trucks that carry them to retail centers, convenience stores, vending machine suppliers, and international shipping hubs. Throughout the entire process, food safety and quality control are paramount. The factory floor is governed by strict hygiene protocols. Employees are required to wear sanitary gear, and the equipment is sanitized regularly using automated clean-in-place systems. Random sampling is conducted at every critical control point, from chocolate refining to shell thickness to final packaging. Laboratory testing checks for microbial contamination, allergen presence, and chemical composition. Quality assurance teams also perform taste tests, structural integrity tests, and heat resistance trials to ensure the product meets Mars Inc.'s global standards. In the case of peanut or almond M&Ms, the process is similar but begins with nut preparation. Peanuts, for instance, are roasted in-house to develop their flavor and reduce microbial load. They are then cooled, sorted by size, and coated in a preliminary layer of chocolate before undergoing the same sugar shell layering process. Their irregular shape requires adjustments to coating speed and rotation patterns to ensure even coverage. The engineering behind M&M production is not only a marvel of food science, but also a study in high-speed manufacturing. Thousands of M&Ms can be produced every minute, yet each one must look and taste exactly the same. This requires the coordination of multiple disciplines: mechanical engineering, chemistry, automation, logistics, and sensory evaluation. The process begins not with whole potatoes, but with dehydrated potato flakes and potato starch. These form the base of the Pringles dough. The flakes are manufactured off-site through a separate drying process where peeled, cooked potatoes are mashed and then passed through drum dryers to remove water, creating thin, crisp sheets of dried potato. These are ground into fine granules and delivered to Pringles production facilities in bulk quantities, stored in climate-controlled silos to maintain moisture levels and prevent clumping. To this potato base, manufacturers add a precise blend of rice flour, corn flour, and wheat starch. This multi-starch formula gives Pringles their distinctive light, yet durable crunch, firmer than a classic chip, but less dense than a cracker. Each ingredient is selected for its functional properties. Rice flour contributes to lightness and reduces oil absorption. Corn flour provides structure and contributes to the crisp texture. Wheat starch acts as a binding agent and helps form the dough into a cohesive sheet. Inside the factory, these dry ingredients are metered into high-capacity industrial mixers. Water is added gradually, and the mixture is agitated until a cohesive dough forms. The consistency of the dough is critical. It must be pliable enough to be rolled and shaped, yet stiff enough to hold its form during frying. Too much water would cause the crisps to bubble and deform. Too little, and they would crack or crumble during processing. After mixing, the dough is conveyed onto a series of steel rollers in a sheeting machine. These rollers press the dough into a continuous, thin sheet, typically about 0.7 to 1 millimeter thick. The uniformity of this sheet is crucial, as even slight thickness variations can affect how the chips fry, blister, and brown. Advanced sensors mounted near the rollers continuously monitor sheet thickness, feeding data to the control system, which makes micro adjustments in real time. Next, the sheeted dough passes under a rotary die cutter. This is a cylindrical cutter with thousands of identically shaped molds engraved into its surface. As the sheet moves beneath it, the die cuts out dozens of curved oval crisps at a time, each one precisely measured to match Pringles' iconic dimensions, around 6.5 centimeters long and 5.5 centimeters wide, shaped with a unique double-curved profile known as a hyperbolic paraboloid. This mathematical shape isn't just aesthetic, it offers stackability, strength, and an audible crunch due to its uniform stress distribution. The dough scrap that remains between the cutouts is immediately separated and returned to the beginning of the process. Conveyor belts collect and transport the unused dough back to the mixer, where it is reincorporated into fresh dough. This closed-loop system minimizes waste and ensures efficiency in ingredient usage. Once cut, the raw crisps are gently lifted from the sheet using suction cups or air jets and placed onto a moving metal belt composed of dozens of concave molds. Each mold perfectly matches the chip's final saddle shape. This belt then moves the raw crisps into the fryer, an enormous stainless steel bath filled with hot vegetable oil, maintained at a consistent temperature of around 170 to 180 degrees. The crisps are submerged for approximately 11 seconds, long enough to remove moisture and induce a Maillard reaction, giving them their light golden brown hue and toasty flavor. Unlike traditional deep-fried potato slices that can curl, bend, or form bubbles, the Pringles molds maintain each crisp's structure during frying. Because the crisps are uniformly thin and precisely shaped, they fry evenly with no dark spots or oil saturation. Excess oil is quickly removed as the crisps exit the fryer and pass over a series of vibrating conveyors and air knives, high-pressure jets that blow away any surface oil or crumbs. At this point, the freshly fried crisps are hot, dry, and unseasoned. They move into the seasoning tunnel, a long, rotating drum equipped with sprinklers or spray nozzles. Here, flavor powders, ranging from classic original to sour cream and onion, cheddar cheese, or barbecue, are evenly applied as the crisps tumble and rotate. The flavor powders are formulated to stick to the crisp's surface via residual oil left from frying. In some varieties, additional ingredients such as powdered cheese or dehydrated vegetables are included in the seasoning blends. To prevent flavor loss and preserve freshness, the seasoned crisps are quickly cooled using forced air systems before entering the packaging phase. This cooling is critical. If the crisps are too warm, condensation can form inside the package, leading to soggy chips and microbial risk. Once cooled, they are conveyed to the stacking and canning line. This is where another defining feature of Pringles becomes prominent: their tubular canister. The stacking machine uses a system of synchronized mechanical arms, optical sensors, and robotic paddles to stack crisps one by one into perfectly aligned columns. This process is remarkably fast and precise. A sensor verifies each crisp's shape and orientation before it's inserted into the growing stack. Once a full stack reaches the correct height, typically around 80 to 100 crisps, depending on the packaging size, it is inserted vertically into a cardboard can that's been pre-formed and lined with a metallized film to prevent oil seepage and moisture intrusion. Each can is equipped with a plastic bottom, which is ultrasonically welded or heat sealed in place before filling. After the crisps are inserted, a foil lid is applied and hermetically sealed using induction heat or pressure bonding to ensure an airtight closure. A plastic snap-on cap is then placed on top, providing resealability for consumer convenience. The filled cans are then labeled and date-coded. Each can receives a printed batch number and expiration date to ensure traceability throughout the distribution chain. Vision inspection systems scan each can to ensure it is filled to the correct level, sealed properly, and free of any external defects like dents or mislabeling. Cans are grouped into multi-packs or cartons by robotic arms and placed on pallets for storage or shipment. Depending on demand and product line complexity, different varieties of Pringles may be produced in separate production runs on the same line, requiring quick and thorough cleanouts between batches to prevent flavor cross-contamination. From here, Pringles are shipped to distribution centers, retailers, and convenience stores across the globe. Thanks to the uniform shape and rigid packaging, they travel exceptionally well, with minimal breakage compared to traditional bagged chips. This durability, coupled with the brand's distinct identity, has made Pringles a staple in global snack markets. Sanitation and quality control are central throughout the process. Each stage of production, from dough mixing to final packaging, is monitored by automated control systems and human operators. Random samples are collected for lab analysis to check moisture levels, oil content, seasoning distribution, and texture. Microbial testing ensures no contamination occurs during handling. Metal detectors and X-ray machines inspect each can before shipping to catch any foreign objects that may have entered the line. Allergen controls are strictly enforced, particularly when switching between varieties like original and cheddar cheese. In addition to ensuring food safety, the factory design and equipment layout support continuous cleaning. Many machines feature clean-in-place systems that pump sanitizing fluids through the equipment without requiring disassembly. Air filtration systems and positive pressure rooms minimize the risk of dust and airborne contaminants affecting product quality. Beyond the manufacturing floor, the creation of new Pringles flavors and formats involves food scientists and R&D specialists who develop seasoning blends, test mouthfeel, and conduct sensory panels with trained tasters. Innovations like Pringles Wavy or Pringles Scorchin follow the same base process, with minor adjustments in dough formulation or seasoning protocols. Despite their high-tech origin, Pringles still deliver a simple satisfaction, a crisp, flavorful bite that feels familiar and fun. But behind that enjoyment is a complex dance of precision equipment, mathematical shaping, and carefully designed formulations. From powdered potatoes to perfectly stacked crisps, every Pringle is a product not just of flavor, but of industrial ingenuity. A testament to how food science can transform something as humble as a potato into a globally recognized snack. Production begins not with the ice cream or chocolate coating, but with the preparation and standardization of raw dairy ingredients, the core foundation of the Magnum bar. Tankers filled with fresh milk and cream arrive at the factory loading bay in refrigerated vehicles maintained at just above freezing point, typically around 2 degrees to 4 degrees. The incoming dairy is immediately transferred into holding silos, where it is kept agitated to prevent fat separation and bacterial buildup. Before the milk is accepted into the process line, samples are extracted for rapid testing. Parameters such as butterfat percentage, total solids, protein content, microbial load, and even somatic cell counts are analyzed using on-site laboratories equipped with infrared spectrometry and bacterial plating systems. This ensures the milk meets the stringent quality criteria set by the manufacturer. Once approved, the milk and cream are blended in precisely calculated ratios to form the base of the ice cream mix. This balance is critical. Magnum ice cream is known for its smooth, luxurious texture, which relies on the right combination of fat and milk solids, not fat. At this stage, additional ingredients are introduced into the stainless steel batch tanks. These include liquid glucose, sugar, stabilizers like gargum or carrageenan, emulsifiers such as mono, and diglycerides, and often milk powders to enhance texture. Each component is metered in via automated dosing systems controlled by a programmable logic controller network that ensures exact proportions are met with less than 1% variance. The mix is then subjected to the pasteurization phase, one of the most critical steps for both safety and stability. Using a high-temperature, short-time pasteurizer, the mix is heated rapidly to a temperature between 82 degrees C and 85 degrees C, and held for around 15 seconds before being cooled immediately to below 4 degrees C. The heat exchanger used here consists of a series of plates and counterflowing heat exchange fluids, enabling rapid thermal shifts with minimal energy loss. This thermal treatment not only destroys harmful pathogens, but also hydrates the proteins and dissolves the stabilizers, enabling them to function optimally in the frozen matrix. Immediately following pasteurization, the ice cream mix enters the aging tanks, large, jacketed vessels where the blend is cooled to 2 degrees and held for a period ranging from 4 to 24 hours. During this aging phase, fat globules begin to crystallize and stabilizers achieve full hydration, which contributes to the mix's viscosity and improves overrun control during later aeration. Gentle agitation is maintained throughout the aging cycle to prevent fat separation and sedimentation of solids. Temperature, viscosity, and bacterial counts are routinely logged by inline sensors, and samples are drawn periodically for consistency checks by quality control technicians. Once the mix has aged sufficiently, it is pumped into the continuous freezer, where it is simultaneously frozen and aerated. The continuous freezer is essentially a cylindrical barrel surrounded by a refrigerant jacket and equipped with rotating scraper blades that keep the ice crystals fine and uniform. As the mix enters, air is injected under pressure to introduce controlled overrun, the percentage of air relative to the base volume. For Magnum, overrun is kept relatively low to preserve a dense, indulgent texture. The mix exits the freezer at a temperature of around 5 degrees to 6 degrees, partially frozen with fine ice crystal dispersion and a soft serve consistency. It is at this stage that the Magnum bar begins to take shape. The semi-frozen mix is deposited into precision-engineered molds made of Teflon-coated stainless steel. These molds are pre-cooled to below for 30 degrees Celsius using glycol-chilled coolant lines that snake underneath the mold platforms. The cold contact causes the outer layer of the ice cream to harden instantly upon deposition, creating a skin that helps maintain structural integrity during demolding. After filling, the molds pass through an inline freezing tunnel maintained at approximately 40 degrees. Powerful blast freezers accelerate the hardening process, ensuring the internal temperature of the bars reaches at least 18 degrees within minutes. This rapid hardening locks in microstructure and minimizes crystal growth, which is essential for a creamy mouthfeel. Next comes the critical stick insertion step. As the bars harden, robotic arms fitted with heated insertion heads press sterilized wooden sticks into each bar's center. The sticks are kept in sealed hoppers and sterilized using either UV light or steam before being transferred via pneumatic feeders into position. Stick alignment must be precise to ensure each bar can be lifted cleanly during demolding and inserted into packaging later. Sensors beneath each mold cavity confirm insertion depth and orientation. Any bars failing this check are automatically diverted for rework. With the wooden sticks now firmly embedded and the bars fully hardened in their molds, the next major phase in Magnum ice cream production is demolding, a delicate process requiring split-second precision and advanced mechanical coordination. At this point, each bar is a solidified mass with a hardened exterior, but still susceptible to temperature variation and surface damage, making the demolding system one of the most finely tuned components on the line. The frozen molds containing the bars are inverted and brought into alignment with a series of vertical actuators mounted above a conveyor system. These actuators grip the wooden sticks gently using silicone-coated clamp mechanisms, applying a consistent amount of pressure to avoid cracking the ice cream body or loosening the stick. Once the sticks are securely held, a stream of warm air or a brief spray of heated glycol solution is applied to the outside of the metal molds, typically in the range of 10 to 20 degrees Celsius, just enough to slightly loosen the outer ice cream surface from the mold walls without melting. This rapid and uniform temperature shift allows the bars to slide out cleanly under the force of the actuators pulling upward. Each demolded bar is then transferred, still suspended by the stick, to a moving belt designed to hold them upright and evenly spaced. This belt is made from food-grade material and includes individual slots or grips to maintain alignment through the upcoming coating process. From here, the bars proceed to the most visually iconic and technically demanding part of the entire operation: chocolate enrobing. The enrobing station is a tightly controlled, enclosed chamber where a continuous waterfall of molten chocolate flows in a recirculating loop. The chocolate used for Magnum bars is distinct in composition. It contains a high cocoa butter content and minimal added waxes, giving it that crisp snap upon biting. Before entering the enrober, this chocolate is tempered in a dedicated system that brings it through specific heating and cooling curves to create stable Type 5 cocoa butter crystals. This phase is essential for producing a glossy finish and preventing fat bloom. As each bar approaches the chocolate curtain, the conveyor briefly halts in precise synchrony with the dipper arms. These robotic arms tilt the bar downward and plunge it swiftly but smoothly through the chocolate bath. The immersion lasts only a fraction of a second, typically under 2 seconds, but during this time, the entire surface of the ice cream is coated uniformly. The mechanics of the dip are choreographed down to the millimeter to ensure that the stick remains free of chocolate while the coating reaches every part of the ice cream body. Upon exiting the bath, the chocolate instantly begins to set. Because the ice cream beneath is so cold, typically 18 degrees C or colder, the chocolate experiences rapid thermal shock, hardening into a crisp shell within seconds. As the bars emerge, air knives blow across their surfaces to remove excess chocolate and shape the outer layer evenly. Some versions of Magnum bars receive additional textures at this point. Chopped almonds, hazelnuts, or cookie bits are showered onto the wet chocolate using vibratory dispensers and light vacuum suction to ensure adhesion. Each of these inclusions has been pre-treated, either toasted, coated, or dusted to resist moisture, so they do not soften or degrade upon freezing. Once coated, the bars advance into a second freezing tunnel. This blast freezer ensures that any heat absorbed during the enrobing process is neutralized and that the chocolate shell sets perfectly around the contours of the bar. The freezer runs at temperatures near 45 degrees C and utilizes directed airflow systems to avoid creating turbulence that might blemish the chocolate surface. The duration of this pass-through varies by bar size and coating thickness, but generally lasts between 90 and 150 seconds. During this time, quality control cameras mounted along the exit conveyor scan each bar for coating defects, streaks, or deformations. After this final freeze, the bars are conveyed to the wrapping area. Each bar is gripped gently by a robotic picker on its stick and placed into the infeed of a flow wrapping machine. The wrapping film, printed with branding, flavor variants, production dates, and barcodes, is unrolled, formed into a tubular shape, and sealed around the bar in one fluid motion. Heat-sealing jaws cut and crimp the ends, creating an airtight pouch. The wrapping material is typically a metallized film laminate designed to block out moisture, light, and oxygen, all enemies of both texture and flavor in frozen products. Inline check weighers ensure that the bars fall within strict weight tolerances. Deviations can result from uneven chocolate coverage or improper portioning in the mold stage. Any over or underweight bars are rejected and sent to a rework station where they are melted down and reincorporated into the system after appropriate quality checks. Properly wrapped bars are then grouped by flavor and SKU using high-speed diverters and placed into cardboard trays or cartons, which are sealed, labeled, and barcoded using automatic case packers. These cartons are loaded onto pallets using a robotic palletizer programmed for weight distribution and cube efficiency. Before exiting the production area, pallets are shrink-wrapped and tagged with RFID or QR codes for tracking. The full pallets are transported by forklift or automated guided vehicle to blast freezers for storage. These freezers are held at 225 degrees and are designed for rapid inventory turnover. Each pallet's temperature history, production time, ingredient batch, and destination are logged in a centralized warehouse management system. First in, first out algorithms control shipment priority, ensuring that no bar stays in storage longer than necessary, preserving texture and freshness. After the bars have been securely wrapped and palletized, they transition from the manufacturing floor into the factory's frozen storage network, a critical intermediary stage in the Magnum production chain where both product preservation and logistics optimization begin to converge. This cold storage system is far more than a simple deep freezer. It is a highly orchestrated environment equipped with real-time telemetry, precision airflow distribution, and digital inventory tracking, ensuring every bar remains at its peak state before being dispatched for delivery. The storage freezers are typically divided into temperature-zoned areas ranging from 18 degrees C to 25 degrees, optimized for different product formats and packaging densities. High-density SKUs, such as multi-pack bars or bulk retail boxes, are placed in the coldest zones to maximize shelf life stability, while single-serve impulse items are stored in slightly warmer zones to streamline short-term logistics. Inside these freezers, robotic retrieval arms or guided forklifts transport pallets to predefined shelving zones. Each zone is outfitted with infrared thermometers, humidity sensors, and airflow regulators to prevent condensation or ice buildup that could damage the cartons or weaken the sealed film barrier. While in cold storage, automated warehouse management systems continuously monitor inventory age, rotation, and batch performance. Every bar remains fully traceable, with its exact ingredient batch, mold cavity, coating time, and line number recorded through an integrated MES. If a quality issue were to arise, this traceability allows technicians to isolate affected bars within seconds. Cold chain integrity is paramount, and sensors embedded in the pallets or wrapping log temperature conditions during the entire resident's time in storage. Any deviation from the defined range triggers alerts and flags the inventory for quarantine and inspection. Parallel to this storage phase, a rigorous battery of quality control procedures operates both during and after the production cycle. Finished Magnum bars are randomly pulled from the line at hourly intervals and sent to a dedicated sensory and analytical lab adjacent to the main production hall. Here, the bars undergo visual inspection for coating uniformity, structural integrity, and shape conformity. The thickness of the chocolate coating is measured using ultrasonic or caliper-based micrometers, ensuring consistency within tenths of a millimeter. Next, the bar is cross-sectioned and photographed under high-intensity lighting to assess internal layering. The core ice cream must remain perfectly centered. The chocolate shell must be crack-free, and any inclusions must be uniformly embedded without pooling or dislocation. Textural analysis is conducted using penetrometers and force feedback probes that measure the pressure required to fracture the shell and bite through the ice cream core. These metrics are compared against benchmark values set during product development to confirm mechanical mouthfeel. Sensory testing panels evaluate the flavor profile using controlled booths designed to minimize environmental bias. Trained tasters assess chocolate intensity, creaminess, sweetness, and aftertaste on a standardized scale. Each sample is anonymized and scored, with deviations outside the preferred range prompting a production review. In parallel, chemical analysis is carried out on composite samples to verify fat content, moisture, overrun, sugar distribution, and microbiological purity. All this data is fed into a central quality dashboard for real-time decision-making. To ensure that production machinery remains precisely calibrated, regular line audits are performed. Each depositor, enrober, stick inserter, and flow wrapper is assigned a maintenance interval based on output cycles. Lubrication, part alignment, and temperature consistency are checked on a rotating basis. For example, chocolate temperature sensors in the enrobing curtain are calibrated weekly against certified thermometers, while the stick insertion depth is confirmed with laser displacement sensors that log each bar's stick angle and alignment. Product variations such as Magnum Double Caramel, white chocolate, almond, or vegan require even more detailed calibration. When switching from one flavor to another, all pipes, nozzles, and hoppers are flushed using food-grade cocoa butter or neutral base mix to avoid cross-contamination. Lines are then sanitized using automated clean-in-place systems that circulate heated detergent and rinse solutions through every component that touches product. Once cleaning is complete, allergen swabs and ATP bioluminescence tests verify cleanliness at microscopic levels before new production begins. Every variation also requires a recipe file update in the PLC that governs the line. The chocolate enrober must adjust flow rate, curtain height, and bath temperature. The depositor head must modify mix viscosity settings. Even the stick length might differ for some variants, prompting a change in insertion arm programming. These configuration changes are downloaded from a master control system, and operators confirm each one through a validation checklist before resuming operation. As the bars prepare for outbound shipping, one of the most critical phases begins: maintaining cold chain logistics during transport. The pre-loaded pallets are transferred directly into refrigerated trucks or shipping containers via insulated loading docks. These vehicles are pre-cooled to the precise temperature specifications required for Magnum bars, usually between 20 degrees and 25 degrees C. Internal air circulation systems ensure even cooling throughout the trailer volume, avoiding temperature stratification that could impact bars located farther from the cooling unit. Each shipment is accompanied by a set of digital loggers that record temperature, humidity, and transit shocks every few minutes. This data is transmitted via GPS or cellular networks to the logistics center, where fleet managers monitor every vehicle en route. If a truck's internal temperature climbs beyond safe levels due to equipment failure or unexpected delays, contingency protocols are activated, rerouting the shipment to the nearest cold facility or triggering a recall. These protections help preserve the critical texture and taste of every Magnum bar, which can be compromised by even a single degree of fluctuation for extended periods. Distribution partners receiving these shipments are required to adhere to strict unloading protocols. Products must be moved from truck to freezer in less than 20 minutes, with continuous temperature logging. Many larger retailers use automated freezer loading docks to receive pallets without breaking the cold chain, scanning barcodes to match inventory with preset planograms and shelf life tracking systems. Smaller vendors or international importers are provided with insulated container modules that extend cold hold time even during manual unloading. All these back-end systems are orchestrated to ensure that when a consumer opens a Magnum bar at home, in a store, or from a vending freezer, the product inside offers the exact experience intended by its designers. The chocolate snaps sharply and cleanly. The ice cream is dense, creamy, and never icy. The stick is sturdy and splinter-free, and the flavor balance, whether it's almond, white, vegan, or double chocolate, is consistent down to the smallest nuance. As we enter the final phase of Magnum's industrial journey, the spotlight shifts to the design, packaging, sustainability integration, and long-term innovation strategies that make this ice cream bar not just a consumer favorite, but a symbol of precision food engineering. Packaging is often the first physical interaction a customer has with the product. And for Magnum, the outer wrap is designed with both functional and sensory intent. The laminate films used in Magnum's wrappers are multi-layer composites combining polyethylene, polyester, and aluminum foil or metallized film. These layers provide high oxygen and moisture barriers while maintaining flexibility, printability, and cold resistance. The films arrive at the facility in massive master rolls, which are stored in climate-controlled zones to prevent curling or brittleness before use. These rolls are mounted on automated unwinding systems on the packaging lines. Each sheet is tensioned and aligned using servo-driven guide rollers that correct for any drift to ensure that the printed graphics stay centered on each bar. The horizontal form-fill-seal machines then synchronize with the bar infeed, wrapping the film around the bar at high speeds, typically over 300 bars per minute per line. The film is heat-sealed using crimp jaws heated to precise temperatures. These jaws not only seal the horizontal seam, but also create tight folds at the ends of each wrapper. An integrated thermal printer marks each wrapper with production codes, expiry dates, and traceability information in real time. Any deviation in seal integrity or print clarity is detected by vision systems and ejected immediately from the belt. Magnum's packaging is also designed for efficient secondary handling. Cartoning machines group bars into branded trays or cartons, depending on whether they're intended for multi-pack retail formats, food service channels, or promotional displays. The cartons themselves are formed from pre-die cut blanks, glued using food-safe adhesives, and sealed under pressure rollers to ensure structural rigidity, especially under frozen conditions. Cartons are also barcoded and batch-coded before being automatically palletized. To minimize environmental impact, Magnum's production sites have embraced aggressive sustainability benchmarks. These include transitioning to recyclable wrappers, reducing water usage per unit of product, and optimizing energy usage across refrigeration and process heating systems. Some facilities utilize ammonia-based refrigeration systems, which are more energy efficient and environmentally safer than legacy hydrofluorocarbon coolants. These chillers are integrated into the factory's centralized energy management system, which tracks kilowatt-hour consumption per production line and flags anomalies for maintenance teams. Heat generated from the pasteurization units, chocolate tempering systems, and compressors is recaptured via heat exchangers and redirected to pre-warm cleaning water or maintain ambient air temperatures in cold season operations. Additionally, LED lighting systems, motion sensor-based equipment activation, and variable frequency drives on motors are now standard throughout newer Magnum production lines to reduce electrical draw without sacrificing throughput. Packaging waste from trimmings or rejected wrappers is segregated and sent to authorized recyclers. Water used in cleaning the production lines is filtered and either treated on-site for reuse in non-contact applications or diverted into municipal treatment systems. All chemical detergents used in the clean-in-place cycles are selected based on both efficacy and biodegradability, and CIP cycles are optimized to minimize volume and time. Compliance officers track and log every cleaning session, ensuring GMP protocols are upheld to the letter. Research and development teams operate parallel to these manufacturing units in dedicated pilot plants, where miniature versions of the full production line exist. Here, small batch runs of experimental flavors, textures, or formats are tested. The pilot lines feature modular enrobing stations, adjustable mold sizes, and programmable depositor heads, allowing developers to explore new bar geometries or formulations without halting mainline production. These facilities are used to prototype new flavors like raspberry swirl cores, coconut infusions, or vegan formulations using pea protein or oat milk bases instead of dairy. Each prototype goes through a consumer panel, sensory profiling, and technical evaluation. Key considerations include melt behavior, shell adhesion, storage resilience, and whether the innovation is compatible with existing high-speed equipment. If a prototype passes all technical and consumer thresholds, it is then scaled up through pilot runs, gradually working toward full line integration. Magnum's manufacturing is also guided by real-time market analytics. Sales data, customer reviews, social media sentiment, and regional purchasing patterns feed into a centralized AI-driven dashboard. If a particular flavor sees a spike in demand or begins trending online, factories can ramp up its production within days. Conversely, if a defect is detected in a particular batch at retail, such as chocolate bloom, stick misalignment, or meltback, data from returned product is fed back into the quality assurance loop, triggering traceability reports and production recalibrations. The relationship between consumer feedback and factory action is immediate and quantifiable. Even packaging redesigns are influenced by heat maps showing where consumers tear wrappers, how easily they peel open a flow wrap seam, and which color schemes attract attention at freezer doors. Augmented reality is even used in some pilot factories to train operators on machine adjustments based on simulated alerts, ensuring they respond faster and more accurately to mechanical or ingredient-related shifts. By the time a Magnum bar reaches the freezer section of a retail store, it has been shaped by hundreds of coordinated systems: robotics, thermal engineering, food chemistry, material science, logistics, and data analytics. It is more than just an indulgent ice cream on a stick. It is the result of advanced cold manufacturing, sustainable process design, and real-time global demand orchestration. Every bite, every snap of chocolate, every silky spoonful of ice cream is engineered to deliver an exact sensory profile, time and time again. The production of Domino's Pizza begins not in the store kitchens, but in massive regional supply chain centers, where the ingredients, particularly the dough, are produced in industrial quantities with an emphasis on consistency, quality, and efficiency. Before any pizza reaches the oven in a Domino's franchise, it starts its journey in these highly controlled factory environments where each element is formulated to exact specifications. The first and most critical component is the dough, which is made fresh daily in these centers and delivered under cold storage conditions to every Domino's outlet. The dough-making process begins with the arrival of bulk ingredients, including high-protein wheat flour, water, vegetable oil, yeast, sugar, and salt. These ingredients are stored in separate storage systems based on their physical state and volume requirements. Flour is kept in massive silos connected to the production floor through pneumatic tubing systems. These tubes transfer flour directly into the industrial-scale mixers with precise weight measurements, controlled by automated batching systems. Water, which must be maintained at a specific temperature range to activate the yeast properly, is stored in stainless steel tanks connected to digital flow meters. This ensures the exact volume is dispensed into each batch, typically to within 1/10 of a liter. Vegetable oil, sugar, salt, and yeast are also dispensed through closed-loop systems that prevent contamination while ensuring high-speed delivery and accuracy. The industrial mixers used at this stage are horizontal high-capacity spiral mixers or fork mixers, depending on the location and the specific equipment model in use. Each mixer is designed to handle hundreds of pounds of dough per batch, usually around 400 to 600 pounds. The process begins with dry ingredients being added first, followed by a controlled stream of water and oil. Once the mixture reaches the desired hydration point, the mixer operates at different programmed speeds to knead the dough until it reaches the correct elasticity and gluten development. This usually takes around 8 to 10 minutes, with temperature sensors embedded in the bowl to prevent overheating from friction, which can damage the yeast. As the dough mixes, factory floor operators monitor each batch's time, temperature, and consistency through a computerized interface. Every mixer is part of a larger manufacturing execution system that records batch data, ingredient lots, timestamps, and operator IDs. This traceability system ensures that if a problem ever arises, such as inconsistent rise or poor texture in a batch, managers can track it back to the specific flour lot or mixing time and make necessary adjustments for future runs. Once the dough reaches optimal consistency, it is automatically discharged from the mixer into a dough trough, which is essentially a wheeled stainless steel container that holds the dough until it's moved to the dividing station. The dough is then transferred into a hopper above a hydraulic or rotary dough divider. This machine uses either vacuum-assisted suction or mechanical cutting blades to portion the dough into uniformly weighted balls, typically ranging from 6 to 20 ounces, depending on the final pizza size. Each portion is measured by load cells, digital weighing systems that maintain accuracy within a few grams. These dough balls then proceed to the rounding machine, which takes each divided piece and rolls it into a tight, smooth sphere. This is crucial for creating the internal tension needed for a uniform rise during fermentation. The rounding machine uses rotating plates or belts that apply gentle pressure and a circular motion to the dough. After rounding, the dough balls are dusted lightly with food-grade flour or semolina to prevent sticking, and then placed into oiled dough trays. These trays are stacked and covered with plastic lids or wraps to maintain humidity and prevent surface drying. They're labeled with a printed barcode that includes the production date, time, dough type, and batch number. At this point, the dough enters the proofing phase, which is critical to developing both the structure and flavor of the final pizza base. Proofing occurs in temperature and humidity-controlled rooms, where racks of dough trays are stored for several hours. The ideal proofing conditions are generally around 80 degrees Fahrenheit with 75% relative humidity, although this can vary slightly based on factory location and yeast activity. The yeast begins to consume the sugars in the dough, producing carbon dioxide and ethanol as byproducts. This gas becomes trapped within the dough's gluten network, causing it to expand and develop the characteristic airy, chewy structure. Simultaneously, organic acids and alcohols created during fermentation start to build complex flavor notes in the dough. During the proofing period, plant operators conduct regular checks to monitor dough expansion, surface tension, and even internal temperature using infrared thermometers and visual inspection. Some factories use automated camera systems that scan the trays and calculate proofing progress by measuring the dough's rise and dome shape. Any deviations from the standard profile are flagged for intervention, whether that means extending the proofing time or moving certain trays to a different section of the proofing room. Once the dough reaches the desired level of fermentation, it is moved to the cold storage phase. In this stage, the dough trays are rolled into large walk-in refrigeration rooms, where the temperature is maintained at approximately 2 to 4 degrees Celsius. This halts the yeast's activity and locks in the developed flavor while also preventing overproofing. The chilled dough can now be stored for up to several days, depending on demand at the destination stores. During this time, the trays are rotated to maintain even cooling and are occasionally inspected for signs of over-fermentation or drying. While the dough is being prepared, Domino's is also handling the sauce production in parallel. Tomato sauce is made in separate processing areas, using high-volume stainless steel kettles equipped with agitators and heating jackets. The base of the sauce is tomato paste, which is diluted with water to reach a specific consistency. To this, measured quantities of salt, sugar, oregano, garlic, basil, black pepper, and other proprietary spices are added. Some locations use pre-mixed spice sachets that are batch-coded for accuracy, while others blend the seasoning on-site. The sauce mixture is heated to temperatures between 80 and 90 degrees Celsius to sterilize it and meld the flavors. Once the heating process is complete, it is rapidly cooled using a plate heat exchanger to bring it down to refrigerated storage temperature. usually 30 degrees Celsius, around 4 degrees Celsius. The cooled sauce is then transferred into food-safe storage containers, often in 10-liter or 20-liter units, and sealed with tamper-evident caps. Each container is labeled with a batch code and production date before being staged for shipment alongside the dough. In addition to sauce, the factory prepares other key ingredients, including shredded cheese and select toppings. The cheese used in Domino's pizzas is typically a low-moisture mozzarella, known for its excellent melting properties and stretch. Some supply centers receive the cheese in bulk blocks and shred it in-house using high-speed rotary shredders that slice the blocks into uniform strands. The shredding process includes a light coating of anti-caking agents like potato starch or cellulose to prevent clumping during storage. The shredded cheese is packed into portioned bags, vacuum sealed, and stored under refrigeration. Once all ingredients, dough, sauce, cheese, and prepped toppings are ready, they are organized and loaded into refrigerated delivery trucks. These trucks operate under a tight logistics schedule, making daily or multi-day trips depending on the volume needs of each Domino's franchise store. The internal temperature of each truck is continuously monitored using GPS-integrated data loggers, and real-time data is fed back to the supply center's central operations system. This ensures that if any deviation in temperature or route timing occurs, corrective action can be taken immediately. By the time the products arrive at the store, they are fully prepared and only require assembly and baking. The franchise stores then execute the final steps of pizza preparation, which involves pressing out the dough, saucing, topping, baking, and packaging. However, the factory's role is absolutely central to ensuring that every ingredient arrives at the exact same standard, no matter where the pizza is being made or consumed. Through this centralized and automated model, Domino's achieves consistency at a global scale, while minimizing waste and human error in the earliest and most foundational stages of production. Once the refrigerated trucks deliver the dough, sauce, cheese, and toppings to each Domino's franchise, the handling of those ingredients transitions from centralized factory production to carefully structured in-store processes that continue to follow standardized protocols. However, the factory's influence is far from over at this point. The store-level procedures are engineered to mirror the consistency, precision, and speed found in the supply chain centers, effectively extending the factory environment into each retail location. Inside the store, the first critical action is the proper storage of the dough. As the dough trays arrive straight from cold storage, they are transferred into the store's walk-in refrigerator, where they are kept at a consistent temperature of 2 to 4 degrees Celsius. Each dough tray remains sealed with its identifying barcode, which includes the production batch, date, and shelf life. This code is scanned upon arrival, logged into the store's inventory system, and linked to the store's daily forecast so the staff can prioritize older dough for earlier use, following a strict first in, first out system to ensure freshness and prevent waste. Before the dough can be used for making pizzas, it needs to temper. Cold dough straight from refrigeration is too stiff and contracted to stretch evenly or bake correctly. Therefore, several trays are pulled from the cooler in staggered intervals and placed in a proofing area within the store, typically kept at room temperature for 30 to 60 minutes. During this period, the dough relaxes, allowing the gluten to become more extensible and the yeast to reawaken slightly, which enhances browning and flavor development in the oven. This step also restores some of the softness and elasticity necessary for the dough to perform consistently on the preparation line. The next key phase in the process is dough pressing or hand stretching, which transforms the proofed dough ball into a pizza base. Depending on the store's equipment and regional preferences, Domino's uses one of several standard methods for this. In many high-volume locations, a mechanical dough press is employed. This press is a heated platen system where a single dough ball is centered between two metal plates. With controlled pressure and temperature, the plates compress the dough to the specified diameter and thickness. The brief heat exposure also helps to set the edge of the crust slightly, which prevents overexpansion during baking. Other stores use hand-stretching techniques, which involve manually flattening the dough using the palms and fingertips to create an even disc, often followed by a gentle spinning motion to widen it to the correct diameter. Employees are trained to feel for even dough resistance, check the uniformity of thickness, and ensure the edges are slightly thicker to create the signature Domino's crust ring. Some locations employ a dough sheeter, a machine that flattens dough between two adjustable rollers, which is commonly used for medium thickness crusts or thin crust options. Once the dough is properly shaped and placed on a pizza screen or baking tray, it is ready to be sauced. The sauce comes in pre-measured containers or large bag-in-box systems with pump dispensers, depending on the store's volume. A standardized rotary sauce ladle or domed saucer is used to apply a precise amount of sauce, usually between 90 and 120 grams for a medium pizza. The sauce is spread using a circular motion that stops approximately 1 inch from the crust edge to allow for natural bubbling and rim development during baking. With the base sauced, the next step is the cheese application. Domino's cheese is a proprietary, low-moisture mozzarella blend, optimized for melt, stretch, and browning. The cheese arrives shredded in sealed, chilled bags and is stored in under-counter refrigeration near the prep stations for quick access. Employees use color-coded scoops to portion out exact grams of cheese per pizza size: small, medium, large, or extra large. This consistency ensures that the cheese melts evenly and that the nutritional and caloric values remain standardized. In high-throughput stores, preloaded portion dispensers or weigh scales may also be integrated into the cheese station to reduce time and improve accuracy. Next, the pizza moves to the topping stage. Domino's toppings, such as pepperoni, Italian sausage, mushrooms, green peppers, onions, olives, jalapenos, grilled chicken, and bacon, are kept in ingredient rails with stainless steel pans, maintained at safe refrigeration temperatures using undermounted chillers. Each topping has a designated scoop or set of tongs, and employees are trained to apply the correct amount and distribution per pizza size and recipe. Toppings are applied in a set sequence to ensure even cooking and consistent flavor layering. For example, pepperoni slices are laid edge to edge to cover the surface in a signature circular pattern, while sausage crumbles are more scattered to allow airflow between pieces. Vegetables are typically added last, as their moisture content can impact the crispness of the crust if layered too deeply. Domino's uses laminated guides and portion charts to ensure that every pizza, regardless of who's preparing it, looks, weighs, and tastes the same. With the pizza fully assembled, it is placed onto a conveyor belt oven, also known as an impingement oven. This oven style uses jets of superheated air blasted from top and bottom to ensure even baking. The oven belt is set to a precise speed, generally resulting in a 5.5 to 7 minute bake time, depending on the pizza size and topping density. The oven's digital interface allows staff to select different profiles for thin crust, hand-tossed, deep dish, or extra cheese options. Each profile adjusts air velocity, top and bottom heat ratio, and belt speed to produce the ideal bake for that style of pizza. During baking, several chemical and physical transformations take place. The crust expands slightly from the final stage of yeast fermentation. Steam is released from the sauce and toppings, and the cheese melts and begins to brown through the Maillard reaction. Excess moisture from vegetables is evaporated by the oven's airflow, ensuring the crust remains crisp and doesn't sag. The pizza emerges from the other side of the oven, fully baked and ready for slicing. At the end of the conveyor, pizzas are transferred to a staging counter, where they rest for 20 to 30 seconds to allow the cheese to set slightly. Then, using a rocker blade or circular pizza cutter, employees cut the pizza into standard portions, usually 8 slices for a large pizza, based on Domino's cutting guides. Each pizza is then slid into a branded corrugated cardboard box, which is specially designed with vent holes and moisture-absorbing liners to preserve crispness during delivery. Every box is sealed and receives a printed label generated by the store's order management system. This label includes the customer's name, order number, timestamp, and pizza specifications. For orders placed online or through the app, this also triggers an update on Domino's proprietary pizza tracker, which uses real-time data from kitchen sensors to notify customers of each stage, from dough prep to oven entry, baking, boxing, and out for delivery status. Throughout the day, all these processes are monitored for compliance with Domino's global standards. District managers conduct regular audits using detailed checklists covering dough handling, oven cleanliness, bake quality, topping accuracy, and safety procedures. Additionally, Domino's has built-in kitchen timers and alert systems that ensure no dough is held at room temperature too long, no pizzas sit unboxed beyond the quality threshold, and no ingredients are used past their hold times. Each store's operations are built to match the precision and consistency of the supply chain factories. In fact, many stores undergo periodic retraining sessions to realign their practices with the upstream factory procedures. This ensures that no matter how far the finished product is from the centralized dough production, the final experience to the consumer remains nearly indistinguishable between one location and the next. As soon as a Domino's pizza is sliced and boxed, the journey continues into a carefully engineered phase focused on preserving product quality and maximizing delivery efficiency. At this point, what might appear to the customer as the simple act of putting a pizza in a box and sending it out the door is, in reality, a continuation of Domino's factory-grade systems, refined, tracked, and executed with industrial precision. Each Domino's box is made of specially designed corrugated cardboard, engineered not only to be structurally strong enough for stacking and transportation, but also to allow moisture control and thermal retention. Small vent holes are strategically placed around the box edges to allow steam to escape without sacrificing internal heat. This is critical to maintaining a crisp bottom crust while keeping the cheese and toppings hot and intact during transit. The liners inside some specialty pizza boxes also use grease-resistant coating and moisture-wicking micro layers that reduce sogginess, especially in pizzas with heavier vegetable or meat toppings. Once the pizza is placed in its box, a label is immediately printed and applied. This label contains all relevant details: the order number, pizza type, time of bake, the customer's name and address, and specific cooking instructions if applicable, like extra crispy crust, light sauce, or no cheese. More importantly, the label also includes digital timestamps and batch codes that tie the finished product directly back to every earlier phase of production. These codes link the order to its dough batch, sauce mix, cheese lot, and even the name of the employee who boxed it. This allows full traceability, and in the event of a customer complaint or quality issue, managers can pull up detailed records to investigate and resolve the problem efficiently. The next link in the process is the delivery system, which Domino's has industrialized to a level similar to its supply chain and production operations. Every Domino's location uses a centralized digital system to optimize delivery routes, monitor driver location, and track pizza temperature using estimated time-to-door algorithms. In some urban areas or flagship locations, Domino's even uses thermal sensors and GPS modules in the delivery bags themselves. These sensors ensure that the pizza never drops below the acceptable temperature threshold, typically around 140 degrees Fahrenheit or 60 degrees Celsius, which maintains cheese integrity and topping stability. The delivery bags used are not basic insulated containers. They are purpose-built thermal sleeves with advanced insulation material, sometimes incorporating phase change materials that hold heat without overheating the product. These bags are lined with aluminum and closed with Velcro or zippers to ensure no heat escape. In some pilot programs, Domino's has experimented with electrically heated delivery pouches that plug into the vehicle's charging outlet, maintaining a regulated temperature across the entire delivery window, especially in colder climates. While the pizza is en route, Domino's proprietary pizza tracker remains active. This cloud-based interface receives inputs from multiple sources: the POS system, kitchen sensors, label printer, and delivery dispatch terminal, and creates real-time updates for the customer. As soon as the order is marked out for delivery, a countdown begins based on predictive delivery timing, factoring in distance, time of day, historical traffic data, and driver availability. This transparency not only improves customer satisfaction, but also provides performance data for internal use. Behind the scenes, Domino's aggregates all this operational data into their enterprise-wide performance dashboards. Each store's key performance indicators, such as order accuracy, delivery time, baking efficiency, and customer satisfaction scores, are updated daily. Store managers and regional supervisors review these metrics in regular meetings, identifying trends, deviations, and opportunities for improvement. If a certain franchise location consistently shows slower bake times or increased complaints about cold pizza, it may trigger a maintenance review of the oven system or retraining of kitchen staff. Meanwhile, at the supply chain level, Domino's uses reverse logistics to complete the factory-style loop. Once a delivery is completed, used ingredient bins, dough trays, and empty sauce containers are returned to the regional supply centers on the next inbound truck trip. These items are cleaned, sanitized, and reused according to food safety protocols. Reusable dough trays, for example, go through automated washing systems that use high-pressure jets, detergent, and thermal sanitation to prepare them for the next production cycle. By managing both outgoing and incoming flows efficiently, Domino's minimizes waste and maximizes logistical efficiency, keeping the system sustainable and cost-effective. Beyond the visible kitchen and delivery operations, there is also a sophisticated forecasting and inventory management system that relies heavily on factory data. Using AI and machine learning, Domino's forecasts demand for dough, sauce, cheese, and toppings at each store based on variables like local events, weather, historical order volumes, and even social media trends. This information is transmitted back to the supply chain centers, which adjust dough production and ingredient packaging accordingly. For example, if a city is expecting a snowstorm, the system may predict a spike in delivery orders and increase dough production by 10% for the affected stores. This tight integration between forecasting and factory production minimizes spoilage and overproduction, ensuring that only as much dough and sauce is produced as will be used within a defined freshness window. The same logic applies to toppings and cheese. Ingredients that are nearing the end of their shelf life can be flagged automatically, prompting store managers to run promotional offers or bundle deals to encourage faster turnover. By linking the retail environment back to the factory floor, Domino's achieves a level of responsiveness and precision rarely seen in traditional food service operations. Domino's also incorporates periodic updates and R&D feedback into its manufacturing systems. When a new product is launched, such as a specialty crust or a new line of toppings, the manufacturing centers adapt their formulations and packaging processes to accommodate the change. For instance, a new crust option may require a dough with a different hydration level or proofing profile. In that case, dough mixers are recalibrated, proofing room settings adjusted, and additional QA steps introduced. The product launch timeline includes upstream changes that affect every supply chain center, down to the labeling system and transport logistics. To maintain global brand consistency, Domino's has standardized its production protocols across all countries, yet also incorporates regional customization. For instance, the dough produced in India may include slight formulation changes to better suit local humidity levels or flour types. In Japan, where crust styles vary, dough mixing and resting procedures may be adapted for fluffier or rice-infused bases. However, the core manufacturing principles, precise batching, automated mixing, cold chain delivery, and digital inventory tracking remain consistent regardless of geography. Domino's also performs routine auditing and calibration of their supply chain centers to ensure continued alignment with performance standards. Factory equipment such as mixers, dividers, and temperature control units are subjected to preventive maintenance and calibration checks at regular intervals. Technicians verify dough density, elasticity, and yeast activity using physical measurements and digital readouts. Similar checks are done for sauce viscosity, cheese fat content, and topping moisture levels. These numbers are logged and analyzed to identify any drift from target specifications, allowing corrective measures to be implemented before product quality is affected. Even packaging materials go through quality control. Corrugated boxes are tested for burst strength, fold endurance, and thermal retention properties. Adhesives used for box sealing are food safe and resistant to temperature extremes. The printing quality on labels is monitored to ensure clarity and durability, as these labels serve both customer-facing and internal traceability functions. Everything down to the ink used on packaging is selected for durability under heat and moisture, a testament to the factory-level thinking that permeates the entire Domino's ecosystem.